What if humanity isn't the first advanced civilization to have walked the earth? For centuries, we've told our story as if it began only recently, with Homo sapiens appearing around 300,000 years ago, constructing cities roughly 10,000 years ago, and sending satellites into orbit just over half a century ago. Yet, Earth has existed for approximately 4.54 billion years, and complex multicellular life has only thrived for roughly 600 million. Within that vast span, entire ecosystems have arisen and vanished: the trilobites that dominated the Cambrian seas, the Mesozoic reptiles, and the vast forests and swamps of the Carboniferous. Human civilization occupies roughly 0.0002% of that timeline. From a purely geological perspective, evidence of any previous technological species would be extremely unlikely to survive intact over tens of millions of years. Could we be the survivors of countless civilizations before us? Join the journey to probe the great filter and the buried mysteries of intelligence in our world. The notion may sound like science fiction, yet it has begun to gain traction in scientific circles. In 2018, NASA climate scientist Dr. Gavin A. Schmidt and astrophysicist Dr. Adam Frank of the University of Rochester posed a provocative question in the International Journal of Astrobiology. If an industrial civilization had existed millions of years ago, how could we know? Their work, now called the Silurian hypothesis, suggests that the traces of such a civilization might still persist, though buried deep within the rock record or hidden as subtle anomalies in chemistry and isotopes. Detecting these traces, however, would require looking at the planet in ways modern archaeology and geology rarely do. This question intersects directly with the Fermi paradox. In 1950, physicist Enrico Fermi asked, "Where is everybody?" highlighting the apparent contradiction between the high probability of extraterrestrial life and the complete lack of observable evidence. One proposed solution is the Great Filter hypothesis. Somewhere along the journey, from simple life to interstellar civilization, there exists a barrier so extreme that almost all intelligent life fails to surpass it. Civilization-ending catastrophes, self-destruction, climate collapse, or cosmic impacts could serve as the filter. But what if the filter is not ahead of us, but behind us? What if Earth has already seen multiple rounds of civilizations rise and fall, each failing to survive the test of deep time? If humanity is not the first, finding traces of predecessors is profoundly difficult. Earth's surface is far from static. Continents drift, oceans open and close, mountain ranges rise and erode, and volcanic activity reshapes land masses in spans of tens of millions of years. According to the US Geological Survey, more than 99% of surface rocks older than 200 million years have been recycled by plate tectonics. Any civilization that existed before the dinosaurs over 66 million years ago would likely have left no architectural monuments, no cities, and no roads. Their entire material culture could have been pulverized, buried, or metamorphosed beyond recognition. Yet traces could still exist in subtler forms. Fossil fuel consumption, for instance, leaves detectable carbon isotope signatures. The burning of coal and oil shifts the ratio of carbon 1,2 to carbon 13 inches the atmosphere, creating anomalies preserved in sediments. Modern humans have already increased atmospheric CO2 concentrations by over 50% since pre-industrial times, a spike that future geologists would readily detect in ice cores and marine deposits. If a pre-human civilization had used fossil fuels extensively, a similar signal could exist, albeit millions of years older. Comparable carbon excursions are seen during events such as the Paleocene-Eocene thermal maximum, PET-Prive 6 million years ago, when global temperatures rose 5-8 degrees Celsius over mere thousands of years. While these shifts are currently attributed to natural processes like volcanic eruptions or methane release, some patterns leave room for speculation. Material evidence might also survive in microscopic or chemical forms. Plastics degrade slowly. Certain ceramics and glass can endure if buried deeply enough. Industrial activity concentrates metals in unusual ways. Platinum, nickel, or rare earth elements, deposited in ratios unnatural to geology, could hint at technological processes. Nuclear fission creates long-lived isotopes like plutonium-244, which decays over 80 million years. Uranium enrichment or mining activity could, theoretically, leave measurable isotopic anomalies long after the civilization itself has disappeared. Even accidental contamination analogous to modern pollution could persist as faint signatures in sedimentary layers or mineral deposits. The timing of potential pre-human civilizations is constrained by the Earth's environmental history. Life's complexity has ebbed and flowed with mass extinctions, glaciations, and tectonic upheavals. The Permian-Triassic extinction event 252 million years ago eliminated over 90% of marine species and 70% of terrestrial vertebrates. The End Cretaceous extinction, 66 million years ago, eradicated non-avian dinosaurs in a cataclysm triggered by the Chicxulub asteroid and volcanic eruptions in the Deccan Traps. Any intelligent species emerging before these events would have been subject to extreme environmental pressures capable of causing extinction. Even an industrial period lasting a few million years would likely leave minimal geological or chemical traces due to erosion, tectonic recycling, and sedimentation processes. Oceans add another layer of obscurity. Covering over 70% of Earth's surface, they can submerge entire civilizations. Sea levels during the Cretaceous were often hundreds of meters higher than today, drowning coastal regions where life and technology might concentrate. Any infrastructure built near these now submerged regions could lie buried beneath kilometers of sediment, inaccessible to modern detection. Mountain ranges, too, erode over tens of millions of years, grinding stone monuments and quarries into sand. Geological processes, tectonic recycling, erosion, and sediment deposition act as natural filters that erase most physical evidence of long-extinct species or civilizations. Biology, interestingly, could provide indirect clues. Human activity has altered evolution extinctions, population collapses, domesticated species, and reshaped ecosystems all leave signatures in the fossil record. Similarly, a pre-human civilization manipulating its environment could have left marks detectable in pollen records, abrupt population shifts, or sudden extinction events. Large-scale deforestation, monoculture agriculture, or artificial selection could disrupt ecosystems in ways preserved for tens of millions of years, encoded subtly in soil chemistry and fossilized remains. Even cosmic events would have played a role in filtering civilizations. Asteroid impacts, such as the one forming the Chesapeake Bay crater 35 million years ago, or larger collisions like Chicxulub, could erase societies entirely. Supervolcanic eruptions, global glaciations, and rapid climate swings all represent planetary-level hazards capable of annihilating intelligent life before it can escape its home world. The Earth's history is a violent chronicle of destruction and renewal. Every rising civilization may have faced extinction long before it could make a mark that survives to modern detection. Exploring these possibilities requires a scientific approach far beyond traditional archaeology. Bridging the gap between archaeology's tens of thousands of years perspective and geology's hundreds of millions of years timeline demands interdisciplinary strategies. High-precision isotopic analysis, deep ocean and continental core drilling, and AI-assisted anomaly detection could identify patterns invisible to conventional methods. Chemical, isotopic, and sedimentary irregularities small in isolation might, together, reveal signs of industrial activity long buried by time. The Great Filter can be understood as the combination of geological recycling, mass extinctions, cosmic hazards, and environmental changes that prevent long-term survival of species over geological time. If Earth had previous industrial species, potential evidence might be limited to chemical and isotopic anomalies, unusual metal concentrations, and sedimentary disruptions detectable through careful scientific analysis. Current knowledge of Earth's geological and environmental history suggests that most material traces of such species would have been erased over millions of years, the Great Filter explained. The Great Filter hypothesis extends the question of potential pre-human civilizations to the broader universe. First proposed in 1996 by economist Robin Hanson at George Mason University, it was based on what he called a disturbing statistical paradox. The universe is approximately 13.8 billion years old and contains an estimated 100 to 200 billion galaxies. Each galaxy holds hundreds of billions of stars, many with multiple planets, suggesting that conditions suitable for life are not uncommon. Despite extensive searches for extraterrestrial intelligence, scanning the skies, analyzing exoplanet atmospheres, and listening for radio signals, no confirmed evidence of intelligent life has been found. NASA's Exoplanet Science Institute estimates that the Milky Way alone may host over 100 million planets in the habitable zone. Even if only a small fraction of these planets develop intelligent life, none has yet been detected. Hansen proposed that somewhere along the evolutionary ladder from primordial molecules to interstellar civilizations there exists a barrier, an event or a series of events so improbable or destructive that most life never surpasses it. This is known as the Great Filter. It is not a single obstacle, but a series of potential choke points that can occur at different stages. Abiogenesis, the origin of life, may be extremely rare, leaving many planets sterile despite the abundance of organic molecules. The transition from single-celled to multicellular life may represent another filter. Although multicellularity emerged around 600 million years ago, it took over 3 billion years after life first appeared, indicating the step is evolutionarily difficult. Another possible filter lies in the evolution of intelligence. Homo sapiens may not be unique in cognitive capability, but the development of abstract thought, language, and advanced tool use is rare even among Earth species. Elephants, corvids, and cephalopods display advanced problem-solving skills, yet none have developed technology beyond basic tools. A potential filter also exists in the stage when a civilization acquires the capacity to significantly alter or damage its environment through war, industrial activity, or other technological processes. Examples from human history include nuclear weapons, large-scale deforestation, plastic pollution, and climate change, which demonstrate the potential vulnerability of technologically advanced species. Applying this framework to Earth's deep history opens a chilling perspective. What if previous intelligent species on this planet reached the stage of industry and innovation only to encounter their own great filter? Mass extinction events offer plausible mechanisms. The end Permian extinction, 252 million years ago, erased more than 90% of marine species and 70% of terrestrial vertebrates. The end Cretaceous extinction, 66 million years ago, eliminated the dinosaurs and many other species after a 10-15 kilometers asteroid collided with Earth near present-day Yucatan. Volcanic events such as the Deccan Traps, which erupted approximately 66 million years ago, released an estimated 1 million cubic kilometers of lava, acidifying oceans and triggering rapid climate shifts. Any industrial civilization existing before these cataclysms would have been obliterated, their cities swallowed, their technologies buried under kilometers of sediment or pulverized by tectonic activity. The evidence, if it exists, would be faint. As Dr. Adam Frank, co-author of the 2018 Silurian hypothesis paper, notes, after 10 million years, The direct evidence of our own civilization, our cities, roads, and artifacts would be effectively unrecognizable. Even the most durable materials transform under pressure and heat. Plastics oxidize or fragment. Metals corrode, melt, or amalgamate with surrounding minerals. Concrete reacts with groundwater and carbon dioxide, slowly turning to limestone-like compounds over geological timescales. Any civilization predating the age of mammals more than 65 million years ago would likely have been erased almost entirely by the combined forces of erosion, sedimentation, and plate tectonics. Yet the filter is not limited to geological processes. Environmental collapse may play an equally lethal role. Rapid climate shifts, runaway greenhouse effects, or prolonged ice ages could wipe out civilizations faster than they can adapt. The Paleocene-Eocene thermal maximum, PETM, approximately 56 million years ago, raised global temperatures by 5.8 degrees Celsius in under 20,000 years, triggering ocean acidification and massive carbon cycle disruptions. A technologically advanced species living during such a period would have faced extreme survival pressures, with energy resources, food supply, and infrastructure all vulnerable to environmental instability. Similarly, supervolcanic eruptions like the Toba event 74,000 years ago, which created a volcanic winter and may have reduced the human population to a few thousand individuals, highlight how sudden planetary events can act as filters that decimate populations and technologies alike. Interestingly, cosmic hazards amplify the lethality of the Great Filter. Impacts from asteroids or comets of just a few kilometers in diameter can produce global-scale consequences. The Chicxulub impact, estimated to release energy equivalent to 100 million megatons of TNT, produced tsunamis, firestorms, and a decade-long impact winter. Supernovae within 30 light-years could irradiate the surface, while gamma-ray bursts could strip away the ozone layer, exposing any surface-dwelling species to lethal levels of ultraviolet radiation. The filter, in this sense, is both local and universal earthly civilizations must contend with threats from their own planet and from deep space. Data from exoplanet research also hint at the filter's prevalence. Of the approximately 6,000 confirmed exoplanets to date, only a fraction lie in the habitable zone, with suitable temperatures for liquid water. Even fewer orbit stable, long-lived stars like our Sunday M dwarfs, the most common type of star, often emit intense stellar flares that strip atmospheres and bombard planets with radiation. Venus, with its runaway greenhouse effect, and Mars, with its thin, desiccated atmosphere, demonstrate the fragility of planetary habitability, reinforcing the idea that even planets with life-friendly conditions may fail to sustain civilizations over geological timescales. The Great Filter also reframes the concept of intelligence in evolutionary terms. It is not enough to survive and reproduce. A species must avoid self-destruction while advancing technologically. Dr. Paul Davies, a theoretical physicist at Arizona State University, emphasizes that civilizations may routinely reach what he calls the technological precipice, a point at which innovation outpaces survival capacity. Nuclear weapons, biotechnological manipulation, and artificial intelligence represent modern examples of potential filters that could terminate a species prematurely. In deep time, such events could have repeatedly ended civilizations before they ever broadcast their presence into space. Even more subtly, the Great Filter could operate invisibly through ecological disruption. Industrial-scale deforestation, large-scale agriculture, and domestication of species alter ecosystems in ways that might be preserved in sediment layers or fossil pollen. These disruptions could be faint signatures of previous intelligent life, but their interpretation is ambiguous easily attributed to natural climatic or environmental shifts. Finding such subtle evidence requires a meticulous understanding of Earth's geochemistry, stratigraphy, and paleobiology tools that modern science is only beginning to apply in this context. A planet older than we imagine. Determined through uranium-led radiometric dating of meteorites and the Acasta gneiss in Canada, the planet's oldest known rock, at 4.03 billion years, Earth has existed for a time span vastly exceeding human history. But Earth's timeline is far from a linear progression toward human dominance. The planet's formative billion years were brutal. Between 4.1 and 3.8 billion years ago, Earth endured the late heavy bombardment, during which countless asteroids and comets struck its surface, generating planetary-scale heat pulses, vaporizing oceans, and likely sterilizing any nascent biosphere. Despite this, life returned with astonishing resilience. Microbial fossils discovered in Western Australia's Pilbara Craton, dated to 3.5 billion years ago, provide the earliest confirmed evidence of life, suggesting that organisms arose rapidly once environmental conditions stabilized. By 3 billion years ago, photosynthetic microorganisms had already begun shaping the chemical composition of the oceans and atmosphere. Over the ensuing eons, evolution advanced in fits and starts, producing bursts of complexity and long periods of relative stasis. About 2.4 billion years ago, cyanobacteria triggered the Great Oxidation Event, a process that transformed Earth's atmosphere from an oxygen-poor state to one capable of supporting complex multicellular life. This event reshaped the biosphere, permitting aerobic metabolism and laying the groundwork for the future emergence of animals and plants. During the Cambrian explosion, roughly 541 million years ago, most modern animal phyla appeared within approximately 20 million years, representing one of the fastest known diversifications of life in the fossil record. Intelligence defined here as the capacity for abstract thought, communication, tool use, and eventually technological development is uncommon in the fossil record. Homo sapiens are one lineage of primates, while other life forms existed for billions of years prior. During the Carboniferous period, from 359 to 299 million years ago, high atmospheric oxygen levels peaking near 35% compared with today's 21% and warm, swampy environments produced giant arthropods, including insects with wingspans over 70 centimeters. Amphibians and early reptiles diversified, exhibiting complex locomotion and predatory behavior. The Permian period, 299 to 252 million years ago, introduced mammal-like reptiles known as therapsids, some of which exhibited increasingly sophisticated social structures, potentially providing a platform for advanced cognition. Following this, the Mesozoic era, stretching from 252 to 66 million years ago, saw dinosaurs dominate terrestrial ecosystems for more than 165 million years. Many species displayed remarkable intelligence. Troodon, for example, had an estimated brain-to-body ratio comparable to modern birds and may have engaged in complex social behaviors. The fossil record also indicates nesting strategies, parental care, and hunting coordination. The geological record, however, is an unrelenting eraser. According to the Geological Society of America, Earth's crust completely recycles itself every 300–500 million years through plate tectonics, subduction, and mountain-building processes. Entire continents drift, collide, and fracture over tens of millions of years. The supercontinent Pangaea, which existed around 335 million years ago, began breaking apart approximately 175 million years ago, eventually forming the modern continents. Oceans open and close. Mountain ranges rise only to be ground down by erosion. Any surface civilization predating these tectonic rearrangements would have been buried, dissolved, or otherwise obliterated. Even the most durable artifacts would degrade under the pressure of time. Metals corrode, plastics oxidize, and organic materials like wood or textiles leave almost no trace after millions of years. Concrete and ceramics can survive longer, but would likely become mineralized or chemically altered under heat, pressure, and groundwater flow. Fossilization is selective. Only under highly specific conditions can biological remains persist. In a geological sense, the survival of cities, roads, or industrial machinery for more than tens of millions of years is extraordinarily unlikely, yet traces might remain in subtler forms. Geochemists have long studied isotopic anomalies as records of past activity. For instance, ratios of carbon isotopes, particularly a depletion of carbon-13 relative to carbon-12, can indicate massive burning of fossil fuels or organic matter, a signature of industrial activity. Similarly, unusual concentrations of heavy metals, such as aluminum, platinum, or rare earth elements in sediment layers, may suggest mining or metallurgical processes. Certain persistent synthetic compounds, like polychlorinated biphenyls, PCBs, degrade extremely slowly and could, theoretically, survive in trace amounts within ancient deposits. The challenge is distinguishing these signals from natural geological processes, which often produce similar anomalies. Advances in sedimentary geochemistry and paleoclimatology have opened new possibilities. Modern techniques, such as inductively coupled plasma mass spectrometry, ICP-MS, and X-ray fluorescence, XRF, allow scientists to detect parts per billion concentrations of trace elements in rock layers hundreds of millions of years old. Researchers are applying these methods to search for subtle chemical and isotopic anomalies in sediments, sometimes referred to as technofossils. For example, late Cretaceous sediment layers contain unusual chemical signatures, although no evidence has confirmed any industrial activity by pre-human organisms. The fossil record itself might hold indirect evidence. Unexplained extinctions, abrupt shifts in species distribution, or sudden changes in sediment composition could be signs of ecological disruptions caused by intelligent actors. For instance, unusual charcoal layers could indicate widespread burning, while rapid climate changes in the geologic past, such as the end Triassic extinction event 201 million years ago, might, in part, reflect anthropogenic-like environmental pressures from a vanished species. Modern paleobiologists and geochemists analyze subtle signals such as unexplained extinctions, abrupt shifts in species distribution, sudden changes in sediment composition, unusual charcoal layers, and rapid climate changes, including events like the end Triassic extinction 201 million years ago. Beyond the chemical and fossil clues, the planet itself retains hints of ancient activity in its structure. The patterning of mineral deposits, anomalous isotopic ratios in oceanic crust, and even unexpected magnetic signatures in certain sedimentary layers might betray the presence of past industrial processes. Consider the case of banded iron formations, which record the early interactions of oxygen and iron in ancient oceans. Banded iron formations primarily record interactions of oxygen and iron in ancient oceans. Similarly, structured anomalies in younger strata are studied using geology, chemistry, and planetary history techniques to understand unusual mineral or isotopic patterns in the rock record. Earth's surface undergoes continuous change due to erosion, tectonics, and sedimentation. These processes make it extremely difficult to detect any pre-human civilizations, and any potential anomalies in the rock record must be evaluated against natural geological variation, diagenetic alteration, and long-term chemical cycling to distinguish anthropogenic or intelligent activity from ordinary planetary processes, signs buried beneath our feet. The traces of any pre-human civilization would likely be subtler than surface structures, potentially preserved in layers of rock, sediment, and ice. Earth's crust is dynamic. Plate tectonics, volcanic activity, erosion, and glaciation have reshaped the surface over billions of years, erasing most features. Remaining evidence would primarily consist of chemical or isotopic anomalies detectable in rocks or sediments. Earth's dynamic surface poses enormous challenges for discovery. According to the US Geological Survey, more than 99% of rocks exposed today are younger than 2 billion years, with the majority of oceanic crust formed within the last 200 million years. Continental crust is more stable, but even these regions undergo metamorphism, sedimentation, and mineral replacement over time. Mountains erode, oceans reshape coastlines, and metals corrode or transform into secondary minerals over millions of years. Remaining evidence would primarily be chemical, isotopic, or molecular. Certain geological formations offer rare stability, capable of recording deep-time anomalies. Ancient cratons, such as the Canadian Shield, the Pilbara Craton in Western Australia, and South Africa's Capville Craton, contain rocks more than 3 billion years old, largely untouched by tectonic recycling. Within these cratons, sediments, banded iron formations, and metavolcanic sequences preserve records of atmospheric, hydrological, and biological conditions from Earth's earliest eons. Unusual concentrations of metals like aluminum, titanium, or rare earth elements, as well as isotopic imbalances, can indicate processes not explained by standard sedimentary or igneous activity. Modern science has documented the persistence of industrial signals in geological strata. Humans have left a measurable technofossil record in less than 2 centuries. Plastics, concrete, synthetic dyes, and nuclear isotopes are embedded in sediments worldwide. Studies led by geologists, such as Jan Zalasiewicz at the University of Leicester, support the Anthropocene as a new epoch. Subtle chemical changes are detectable long after deposition. For example, the Fukushima Daiichi nuclear disaster in 2011 introduced cesium-137 and iodine-131 into ocean sediments, traceable decades later. Certain materials are more likely to leave lasting traces. Metals like copper, aluminum, and nickel oxidize over time, but may form mineral assemblages or alloys distinguishable from naturally occurring deposits. Fluoropolymers, chlorinated hydrocarbons, and other synthetic organics can survive in chemically altered forms within sedimentary or metamorphic rocks. Shifts in atmospheric carbon or temperature may also be preserved. During the Paleocene, Eocene thermal maximum, PET-M, around 56 million years ago, global temperatures rose by 5.8 degrees Celsius over approximately 20,000 years, accompanied by the release of 5,000 gigatons of carbon, primarily attributed to volcanic activity and methane hydrate destabilization. Ice cores, deep-sea sediments, and continental shelves provide further archives. Ice sheets in Greenland and Antarctica contain layers spanning hundreds of thousands of years, recording trapped air bubbles, volcanic ash, and dust. Changes in isotopes of oxygen and carbon reveal past temperatures and atmospheric composition. Marine sediments, with accumulation rates of 110 mm per thousand years, trap microfossils such as foraminifera and coccolithophores, which record ocean chemistry at the time of deposition. Industrial activity could theoretically alter these signatures through large-scale carbon emissions, heavy metal contamination, or chemical runoff. Interpreting anomalies in the rock record can be difficult. Massive volcanic eruptions release CO2 and trace metals. Asteroid impacts inject iridium-rich dust. Methane hydrate destabilization rapidly increases greenhouse gases. The Siberian traps, which erupted around 252 million years ago, released an estimated 3 million cubic kilometers of basalt, along with enormous CO2 volumes, contributing to the Permian Triassic extinction. Multidisciplinary analysis, combining geochemistry, paleoclimatology, sedimentology, and materials science, helps distinguish between different geological events. Large-scale deforestation, mining, or irrigation can leave changes in sediment composition or mineral distribution. Palynology, the study of fossil pollen and spores, may reveal abrupt shifts in vegetation. Nitrogen and sulfur isotope ratios can indicate changes in natural biogeochemical cycles. Mass extinctions are associated with significant environmental perturbations, traceable in the sedimentary and fossil record. Theoretical modeling supports the plausibility of detecting such signals. High-resolution isotope analysis shows that even minor deviations can persist in sediments over tens of millions of years under favorable conditions. Oceanic anoxic events, when deep waters become oxygen depleted, can trap metals, hydrocarbons, and organic compounds in concentrated layers, preserving anomalies that may reflect anthropogenic or pre-anthropogenic activity. Similarly, sudden climate events like the PETM provide natural control scenarios to compare against potential industrial signatures. Potential long-term chemical signals in rocks and sediments include unusual isotopic ratios, mineral anomalies, persistent synthetic compounds, or subtle sedimentary changes. Geologists employ techniques such as accelerator mass spectrometry, X-ray fluorescence, and laser ablation, inductively coupled plasma mass spectrometry to analyze ancient cores. Cratonic shields and other long stable continental regions are primary targets, although anomalies are typically small and require detailed analysis. The investigation of potential pre-human industrial activity focuses on identifying chemical, isotopic, and mineralogical anomalies preserved in Earth's rock and sediment layers. Evidence, if present, would likely appear as unusual isotopic ratios, trace metals, or synthetic compounds embedded within stable geological formations such as cratons, deep-sea sediments, long-lived sedimentary basins, and other geologically resilient environments. Detecting these traces requires high-precision analytical methods, including accelerator mass spectrometry, X-ray fluorescence, and laser ablation, inductively coupled plasma mass spectrometry, combined with careful sampling, stratigraphic correlation, and statistical validation to differentiate anthropogenic-like signals from natural geological processes. These studies document variations in sediment chemistry, geochemical cycles, atmospheric composition, and mineral formation processes across vast spans of Earth history. Even the absence of detectable anomalies provides useful information by constraining the temporal and spatial limits of preserved chemical records and revealing the persistence, transformation, and degradation rates of different materials over tens to hundreds of millions of years. Research in this area prioritizes isotopes, trace elements, and molecular residues preserved in deep-time geological archives, offering a framework to quantify chemical and environmental signatures over geological timescales. By examining these measurable markers systematically across multiple locations and rock types, scientists can establish baselines for distinguishing natural geological phenomena from potential industrial-like activity, providing empirical, data-driven insights rather than speculation regarding Earth's distant past. The Silurian hypothesis. In 2018, climate scientist Gavin A. Schmidt of NASA and astrophysicist Adam Frank introduced a strikingly imaginative yet scientifically grounded concept, the Silurian hypothesis. Published in the International Journal of Astrobiology, their paper asked a deceptively simple question: could evidence of an industrial civilization be preserved in Earth's deep geological record? And if so, could we detect it millions of years later? The name was borrowed from the Silurians of Doctor Who, ancient reptilian beings who supposedly ruled Earth long before humans. The homage is whimsical, but the science behind the idea is serious. At its core, the Silurian hypothesis challenges conventional assumptions about time, preservation, and the durability of technology. It is not a claim that pre-human civilizations existed. Instead, it is a framework for evaluating the limits of our ability to detect industrial activity in deep time. Schmidt and Frank approached the question by asking, if a prior civilization underwent an industrial revolution, what traces would remain, and how might they differ from natural geological anomalies? The hypothesis rests on the recognition that Earth's dynamic processes, plate tectonics, erosion, sedimentation, and volcanism, erase almost all surface evidence over tens of millions of years. Modern cities, roads, and infrastructure would be completely destroyed or transformed beyond recognition. However, chemical, isotopic, and molecular residues could persist. The researchers identified several potential fingerprints of industrial activity that could survive deep time. One of the primary markers is isotopic shifts. The rapid industrial-scale burning of fossil fuels releases vast amounts of carbon with a distinctive isotopic signature. In the modern era, the ratio of carbon-13 to carbon-12 inches, the atmosphere has decreased by roughly 1.5 ARIO since the Industrial Revolution. Schmidt and Frank theorized that a similar anomaly could be preserved in ancient carbonates, organic-rich sediments, or ice cores. Additionally, oxygen isotope ratios could reflect abrupt climate shifts caused by energy use, deforestation, or large-scale greenhouse gas emissions. Nitrogen isotopes could also be affected as industrial agriculture and fertilizer alter the nitrogen cycle, leaving potential markers in sediments or preserved organic material. Another potential marker lies in unusual sediment layers. Industrial activity often produces metals, slags, and rare earth elements in concentrations atypical for natural deposition. Sedimentary layers, enriched in elements like aluminum, titanium, or cadmium, or containing synthetic compounds, could serve as long-term markers. Modern analogues include fly ash from coal combustion, which contains trace metals such as arsenic, selenium, and lead, often incorporated into soils and sediments. These layers might appear as anomalous bands in marine or lacustrine sediments, preserved under favorable depositional conditions. Schmidt and Frank also note that even microscale layers could serve as a chemical fossil, a subtle but detectable trace of industrial activity. Moving to another important marker, fossil fuel residues would also leave enduring traces. Hydrocarbons created or modified by human activity are among the most persistent chemical markers. Petroleum derivatives, polyaromatic hydrocarbons, PAHs, and chemically altered kerogen could persist in ancient strata. While natural processes can also produce PAHs, the ratios of certain molecules, such as high concentrations of synthetic polymers, could distinguish biological from technological origins. For example, polyethylene and polypropylene are synthetic polymers almost entirely of anthropogenic origin, and their breakdown products could theoretically survive in altered forms for tens of millions of years. Lastly, synthetic chemical compounds could provide another lasting trace of human activity. Persistent organic pollutants, POPs, such as polychlorinated biphenyls, PCBs, or fluorinated compounds, resist biodegradation and can survive for millions of years in altered forms. Even in highly metamorphosed rocks, chemical signatures can remain embedded in mineral matrices or trapped within sediments. Modern studies have shown that trace amounts of perfluorooctane sulfonic acid, PFOS, and related compounds are now present in soils and sediments worldwide, including areas that are seemingly pristine, demonstrating the far-reaching longevity of synthetic chemicals. To anchor these theoretical markers in reality, Schmidt and Frank compared them to known geological phenomena, the Paleocene Eocene thermal maximum PETM, approximately 56 million years ago. Concurrently, carbon isotope ratios dropped by roughly 3:1, indicating a massive carbon release into the atmosphere and oceans. Mainstream science attributes this event to volcanic activity or destabilized methane hydrates. The PETM provides an example of how large-scale carbon emissions can create a distinctive isotopic anomaly preserved in sediments. Similarly, oceanic anoxic events OAEs of the Cretaceous period around 120–90 million years ago demonstrated sudden drops in oxygen concentrations in deep oceans, accompanied by spikes in carbon and other trace elements. These layers preserve metal enrichments, black shales rich in organic carbon, and subtle isotopic anomalies. Such events show how rapid environmental changes are recorded in the geologic record, providing reference points for analyzing unusual chemical or isotopic signatures in sediments. Concrete, which is ubiquitous in modern infrastructure, breaks down over geological timescales through chemical weathering. Plastics produced at over 400 million tons per year globally fragment into microplastics, some of which may become buried and chemically altered in sediments, while the majority transform into particles indistinguishable from natural detritus. Large-scale nuclear activity produces isotopes such as cesium-137, iodine-129, or plutonium isotopes, which decay or migrate through rock layers over thousands to millions of years, whereas uranium-235 persists as a long-term geochemical tracer. The hypothesis also emphasizes the challenge of distinguishing artificial signals from natural ones. Volcanic eruptions, massive wildfires, asteroid impacts, and methane hydrate releases can all produce carbon isotope excursions, heavy metal enrichments, and sediment anomalies that mimic industrial activity. Distinguishing between natural and technological causes requires multi-proxy analysis, combining isotopic measurements, trace element studies, sedimentology, and molecular fossil detection. Accelerator mass spectrometry, X-ray fluorescence, Raman spectroscopy, and synchrotron-based imaging are all tools that can help detect subtle deviations in ancient sediments, even when primary structures have long been destroyed. Beyond Earth, the hypothesis provides a framework for planetary science. Mars's surface, largely devoid of plate tectonics, could preserve ancient chemical markers. Venus, despite extensive resurfacing, may retain small pockets of ancient crust with isotopic anomalies. Icy moons such as Europa or Enceladus could preserve chemical signatures in subsurface oceans. This interdisciplinary approach, combining geology, chemistry, and astronomy, is referred to as astroarchaeology, the study of detecting technological or chemical activity in the geological record of planetary bodies. Geological studies indicate that within approximately 10 million years, almost all surface evidence of human activity will be eroded, leaving primarily chemical and isotopic traces. Schmidt and Frank's analysis highlights the timescales over which industrial activity can be recorded in sediments, isotopic ratios, and molecular markers, providing measurable signatures for future geochemical and planetary investigations. The Silurian hypothesis provides a framework for assessing the detectability of industrial activity in the geological record. It supports cross-disciplinary research combining geochemistry, sedimentology, and isotopic analysis to identify chemical, isotopic, and sedimentary markers that persist over millions of years. Applied to Earth, Mars, or Venus, this framework identifies the types of measurable geochemical and sedimentary signatures that industrial processes can leave behind in planetary strata. Geological fingerprints of technology. Every technological age leaves an imprint on the planet in the form of chemical, isotopic, and sedimentary anomalies. Geological processes such as mountain formation, erosion, sediment redistribution, and oceanic deposition alter or erase surface structures over millions of years. Modern civilization has already generated detectable signals, including carbon isotope shifts, heavy metal concentrations, and synthetic materials. Scientists investigate how comparable anomalies in deep-time sediments could be interpreted as evidence of industrial-scale activity. One of the most robust indicators is carbon isotope anomalies. The ratio of carbon-13 to carbon-12 inches atmospheric CO2, expressed as delta to the power of 13c, responds to large-scale carbon emissions. Today, human activity releases roughly 37 billion tons of CO2 annually, based on the Global Carbon Project 2023, resulting in a delta to the power of 13c shift of 1.5 U since the Industrial Revolution. These anomalies are preserved in tree rings, peat layers, marine carbonates, and ice cores. In deep-time geology, comparable shifts occur during major events. The end Permian extinction, about 252 million years ago, saw delta to the power of 13c excursions of 310 to 40, reflecting massive carbon input into the atmosphere. Such shifts, when analyzed in sediments, can indicate rapid environmental perturbations recorded in delta to the power of 13c values. Synthetic material deposition provides another durable signal. Modern plastics, which number in the billions of tons globally, gradually fragment into microplastics that integrate into marine sediment. The British Geological Survey 2021 estimates that over 30 million tons of plastic particles are already embedded in the top layers of the ocean floor. Over geologic timescales, these particles may become chemically altered and mineralized, forming thin, polymer-rich layers distinct from natural sediments. Persistent synthetic polymers such as polyethylene and polytetrafluoroethylene, PTFE, could survive for millions of years in altered forms, acting as a unique signature of technological activity. Heavy metals also serve as telltale indicators of industrial influence. Processes like smelting, mining, and manufacturing concentrate metals far beyond natural background levels. Urban soils today can contain up to 500 times the natural abundance of lead, based on the Environmental Science and Technology 2019, with mercury, chromium, and cadmium similarly enriched. Over millions of years, these metals can mineralize into stratigraphic layers distinguishable from naturally occurring ores by their isotopic and elemental ratios. Unusual patterns, such as elevated lead-206 divided by lead-207 ratios or mercury isotopic anomalies, may function as chemical fingerprints, indicating concentrated anthropogenic activity rather than diffuse geologic processes. Radioisotopes present some of the most precise and enduring temporal markers. Nuclear testing between 1945 and 1980 dispersed isotopes like plutonium-239, with a half-life of 24,100 years, and cesium-137, with a 30-year half-life, throughout the atmosphere. Trapped in sediments, ice cores, and soils, these elements will remain detectable for hundreds of thousands of years. If an ancient civilization had developed nuclear energy or weapons, residual radioisotopes with half-lives exceeding 10,000 years could persist in stratified rock layers or subglacial deposits, offering a rare, quantifiable timestamp of industrial activity. Modern studies of radioactive isotopes in Antarctica and Greenland ice cores have already revealed anthropogenic contamination at global scales, confirming that these signatures travel far beyond their points of origin. Industrial agriculture also leaves a subtle but measurable mark. The Haber-Bosch process, developed in the early 20th century, enabled the mass production of nitrogen fertilizers, dramatically altering the nitrogen isotope ratio delta to the power of 15 N in soils. Such shifts are preserved in fossilized soil horizons, lake sediments, and even peat layers. In principle, similar isotopic patterns could indicate large-scale food production by any technologically advanced society in deep time, distinct from the natural cycling of nitrogen through ecosystems. When combined, these elements, isotopic disruptions, synthetic residues, heavy metal concentrations, and radioisotopic anomalies, form what geologists now refer to as a technosignature layer. This composite layer is not merely a single marker, but a correlated set of chemical and mineralogical anomalies that, together, signal industrial activity. For context, NASA scientists studying extraterrestrial sedimentary deposits on Mars look for comparable signatures, layers enriched in unusual metals, anomalous isotopic ratios, or persistent organics. The Perseverance rover's Sherlock instrument, scanning habitable environments with Raman and luminescence for organics and chemicals, is capable of detecting mineral and organic anomalies down to micron scales, demonstrating how planetary science now intersects with the search for technological imprints, a form of astroarchaeology. Even on Earth, researchers are revisiting ancient sedimentary anomalies with renewed attention. For example, Cretaceous-age marine sediments contain elevated concentrations of nickel, chromium, and vanadium, often in localized bands that are difficult to reconcile with typical oceanic or volcanic deposition. Similarly, unusual isotopic excursions in Permian, Triassic boundary sediments, shifts in carbon, oxygen, and sulfur isotopes remain incompletely explained, prompting debate over whether the sources were purely natural, such as the Siberian TRAPS eruptions, or if they may harbor unexplored complexity. While there is no confirmed evidence of prior civilizations, these patterns highlight the difficulty of distinguishing natural from potentially artificial anomalies in deep time. Additional modern examples illustrate the persistence of technological markers. In urban waterways, trace metals and synthetic molecules like polychlorinated biphenyls (PCBs) are already concentrated hundreds of meters below the riverbed. Studies from the US Geological Survey indicate that even in remote regions such as the Arctic, concentrations of microplastics, perfluorinated compounds, and anthropogenic metals are measurable. These observations confirm that technosignatures need not remain. Local industrial civilizations can leave global chemical footprints, further enhancing their detectability over geological scales. The study of these fingerprints has implications beyond Earth. If Mars, Venus, or the icy moons of Jupiter and Saturn ever hosted intelligent species, similar geochemical anomalies might persist in their crusts. For example, the 4.2 billion-year-old Martian crust is relatively stable, with sedimentary deposits in ancient lake beds potentially preserving chemical evidence of hypothetical industrial activity. On Earth, however, plate tectonics constantly recycles crustal material, meaning that only stable cratons, ancient shields, and exceptionally well-preserved marine sediments are likely to retain detectable technosignatures for tens or hundreds of millions of years. Ultimately, geological fingerprints of technology are subtle and can be detected through geochemical, sedimentological, paleoclimatological, and materials science analyses. Advanced instrumentation, including mass spectrometry, X-ray fluorescence, and synchrotron-based imaging, enables measurement of isotopic and elemental variations at fine scales. Small deviations from expected background patterns in sediments can indicate the presence of unusual chemical or mineralogical compositions associated with industrial processes. As the study of technosignatures progresses, technological activity can leave chemical, isotopic, and mineralogical traces over geological timescales. These signatures provide reference points for identifying comparable anomalies in ancient sediments and allow scientists to model the preservation of contemporary human activity in the geological record. Mass extinctions and do-overs. Earth's history includes repeated catastrophic events that significantly altered ecosystems. Over the past 540 million years, The planet has experienced at least 5 major mass extinctions, the Big Five, along with dozens of smaller, ecologically significant die-offs. These events eliminated species at rates exceeding 90% in certain cases. Any prior civilizations, if they existed, would have been vulnerable to such events, leaving minimal physical evidence in the geological record. The Cretaceous Paleogene KPG extinction 66 million years ago is recorded as a global layer of iridium-rich clay, shocked quartz, and microspherules, corresponding to the impact of a 10-12 kilometers wide asteroid near the Yucatan Peninsula. The impact released energy equivalent to approximately 100 million megatons of TNT, causing fires, tsunamis, and a prolonged period of reduced sunlight and cooling. Approximately 75% of species, including all non-avian dinosaurs, disappeared. Any infrastructure from a hypothetical civilization would have been destroyed by these processes. Earlier still, about 252 million years ago, the Permian-Triassic extinction, aptly called the Great Dying, marked the most severe collapse in Earth's history. Approximately 96% of marine species and 70% of terrestrial vertebrates vanished. Researchers from the University of Leeds 2020 have documented evidence that the event was driven by massive volcanism in the Siberian Traps. Over a period of roughly 1 million years, volcanic eruptions expelled more than 300 million cubic kilometers of lava and trillions of tons of CO2, causing extreme global warming, ocean acidification, and widespread anoxia in marine environments. The atmospheric CO2 concentration may have risen from pre-event levels of 1,000 parts per million to upwards of 5,000 parts per million, triggering temperature spikes of 10-15 degrees Celsius. Any civilization existing at that time would have faced near-immediate collapse. Oceans became uninhabitable, land ecosystems transformed into deserts or toxic zones, and the biosphere itself was severely destabilized. The Ordovician-Silurian extinction, around 443 million years ago, and the late Devonian extinction, spanning 359 million years ago, illustrate how environmental stress can operate differently. The Ordovician-Silurian event appears to have been triggered primarily by glaciation and dramatic sea level changes, which led to a collapse of shallow marine habitats. Estimates suggest that up to 85% of marine species perished, particularly brachiopods, trilobites, and reef-building organisms. The late Devonian extinction, on the other hand, seems tied to oxygen depletion in the oceans, bolstered by episodes of widespread volcanic activity in regions that are now part of North America and Europe. Both events left clear chemical and isotopic signatures, abrupt shifts in carbon and oxygen isotopes, sulfur anomalies, and sedimentary evidence of hypoxia, yet, like other mass extinctions, they contain no definitive markers of intelligent activity. What these events collectively reveal is twofold. Earth is extraordinarily volatile, and life is remarkably resilient. After each catastrophe, new ecosystems emerged, often more complex and diverse than before. Following the KPG extinction, mammals diversified and eventually gave rise to the lineage that would produce humans. After the Devonian collapse, vertebrates began to colonize terrestrial habitats in earnest. From this perspective, mass extinctions act as evolutionary bottlenecks, selective sieves that periodically reset the conditions for life to innovate, adapt, and occasionally to produce intelligence. Some researchers even suggest that repeated environmental stress may promote the evolution of social cooperation, problem solving, and tool use. A 2016 study by the University of California, Berkeley, posited that intermittent crises create strong selective pressure for behavioral flexibility, indirectly favoring the rise of intelligence. In this sense, mass extinctions may function as natural filters, a terrestrial analogue to the so-called Great Filter in astrobiology. Yet, while life itself rebounds, technological civilizations are far more fragile. Infrastructure, culture, and artifacts are transient on geological timescales. Even if a planet were covered with cities, roads, and monuments, tectonic activity, erosion, and sedimentation would erase nearly all physical evidence over tens of millions of years. Catastrophic events leave sharp transitions in the geological record, spikes in carbon, temperature, sulfur, or extinction rates, any of which could effectively mask the rise and fall of an intelligent civilization. The absence of artifacts in the deep past, therefore, is not proof that intelligence never existed. It may simply reflect the erasing power of natural processes. Earth's 5 great extinctions, while catastrophic, were not alone. MIT geologists 2018 catalogued at least 19 smaller extinction pulses during the Phanerozoic eon, ranging from the Frasnian-Famennian interval to the Pliocene cooling events. Some of these minor events eliminated 20–50% of species, often linked to asteroid impacts, localized volcanism, or abrupt climate swings. These periodic die-offs illustrate that the planet has repeatedly presented opportunities for civilizations to vanish, without leaving more than faint chemical or sedimentary hints behind. Even today, modern human civilization faces analogues to these ancient threats. Supervolcanic eruptions, such as the Yellowstone caldera, could inject thousands of cubic kilometers of ash into the atmosphere, while asteroid impacts similar in size to Chicxulub occur roughly once every 5,100 million years. Understanding past extinction events is thus not just an academic exercise. It informs our awareness of planetary fragility and the transient nature of civilization itself. For hypothetical pre-human civilizations, the odds of surviving even a single major extinction event were slim, and the probability of persisting across multiple global catastrophes approaches zero. In addition to environmental volatility, preservation bias compounds the problem. Geological processes, subduction, metamorphism, erosion, and sedimentation preferentially erase surface structures, while leaving only subtle chemical or isotopic traces. Fossilization itself is selective, favoring durable skeletons, teeth, and shells over softer tissues or transient human artifacts. The combination of mass extinctions and preservation bias creates a profound challenge. Even if a civilization arose, thrived, and left material evidence, the odds of detecting it hundreds of millions of years later are vanishingly small. Catastrophes and recoveries demonstrate patterns of extinction and ecosystem recovery over geological timescales. Mass extinctions produce measurable chemical and isotopic anomalies in rocks and sediments, which can persist for millions of years even when physical structures or organisms are erased. Fossil records, the incomplete story. The fossil record is both a treasure trove and a mirage. It offers glimpses of life on Earth across billions of years, yet it is notoriously incomplete. Despite the immense diversity of species that have existed, fewer than 0.1% of all organisms are preserved as fossils. This stark paucity leaves enormous gaps in our understanding of life's history and opens the door, at least theoretically, to the possibility that entire lineages, even intelligent ones, might have arisen and vanished without leaving a trace recognizable to modern science. Fossilization is a rare and fragile process. According to the Natural History Museum in London, for an organism to fossilize, several improbable conditions must align: rapid burial in sediment, low oxygen to slow decay, and protection from scavengers or microbial degradation. Hard parts like shells, bones, and teeth are far more likely to fossilize than soft tissues, which degrade within days under normal conditions. Even when these conditions are met, tectonic activity, erosion, and chemical processes often destroy fossils before they can be discovered. Mountain ranges, subduction zones, and volcanic upheavals continuously recycle the Earth's crust, erasing the majority of what might once have been preserved. The oldest confirmed fossils are stromatolites, layered microbial mats found in Western Australia's Pilbara region, dating to approximately 3.48 billion years ago. The span between this microbial origin and the Cambrian explosion, roughly 541 million years ago, is sparsely documented in the fossil record. During this time, microbial life diversified extensively, producing forms such as cyanobacteria that fundamentally reshaped the planet's atmosphere and chemistry, leaving only minimal physical fossils. Fossils provide only a partial view of biodiversity. The Smithsonian Institution estimates that roughly 1.3 million animal species have been formally identified, yet total historical biodiversity is believed to exceed 5 billion species. The vast majority are completely unknown. When it comes to ancient civilizations, the problem is magnified. Archaeological artifacts, human-made structures, and tools decay far faster than bones or shells. Even under optimal preservation conditions, materials like wood, textiles, ceramics, and plastics eventually decompose, leaving behind little more than chemical residues or trace elements. Mathematical modeling demonstrates the rarity of fossil preservation. In 2017, researchers at Duke University simulated fossilization rates and found that even abundant species have less than a 1 in 10,000 chance of leaving a single identifiable fossil after 1 million years. By comparison, the fossil record preserves far more efficiently massive, long-lived, and mineralized organisms such as dinosaurs, ammonites, and corals, explaining the bias toward these groups in deep time studies. Detecting evidence of civilizations older than the dinosaurs would require conditions far beyond typical fossilization probabilities. Geological accessibility further compounds the problem. Much of Earth's surface is obscured by vegetation, soil, water, or modern urban infrastructure. Less than 1% of the terrestrial surface has been systematically excavated by paleontologists. Even monumental fossils and deposits remain undiscovered in unexcavated regions, buried under kilometers of sediment or hidden in inaccessible cliffs and ocean floors. The Burgess Shale in Canada and the Sirius Passet in Greenland are rare exceptions where conditions allowed for soft-bodied fossil preservation, but these represent outliers rather than the norm. Structures, tools, or bones from potential pre-human civilizations would be extremely unlikely to survive in exposed rock formations. Despite these limitations, the fossil record occasionally documents abrupt biological turnovers. The end Triassic extinction to 201 million years ago saw sudden collapses in reptile diversity, with volcanic activity in the Central Atlantic Magmatic Province as a possible trigger. Similarly, the Carboniferous rainforest collapse to 305 million years ago caused ecological disruption, fragmenting tropical forests and driving extinctions of amphibians, insects, and early reptiles. Minor climate oscillations, such as the late Devonian glaciations, also created population bottlenecks in affected species. Preservation bias affects the detection of behaviors associated with intelligence. Fossils showing tool use, social structures, or symbolic behavior are unlikely to be preserved because they involve soft materials or ephemeral constructions. Modern examples illustrate this principle. Octopuses manipulate coconut shells as tools. New Caledonian crows craft hooks to extract insects, and dolphins teach complex hunting strategies, none of which leave direct fossil evidence. In addition, chimpanzees and other primates use sticks to extract termites or stones to crack nuts, behaviors observable over thousands of years but rarely preserved in the archaeological record. Over hundreds of millions of years, comparable or more advanced forms of intelligence could have existed and disappeared without leaving conventional fossils, leaving only chemical, isotopic, or sedimentary traces detectable under exceptional conditions. The fossil record's fragmentary nature is compounded by temporal resolution limits. Stratigraphic layers often amalgamate millions of years of deposition into a single horizon, which can obscure short-lived events or species. Minor extinction pulses, ephemeral populations, or even transient civilizations could easily leave no detectable physical evidence within these coarse layers. For example, the Ediacaran biota, soft-bodied organisms that lived roughly 600 million years ago, are preserved in only a few exceptional sedimentary deposits, such as the Mistaken Point Formation in Newfoundland and the Ediacara Hills in Australia. Similarly, the Cambrian Burgess Shale preserves organisms with soft tissues that elsewhere vanish, demonstrating that preservation is heavily dependent on local depositional conditions and sedimentary chemistry. Geochemical and sedimentary proxies provide measurable avenues for detecting past technological activity. Industrial processes, agriculture, and large-scale resource extraction introduce isotopic anomalies, elevated trace metals, and synthetic compounds into sediments. For instance, microplastic particles as small as 1/5 microns have been incorporated into marine sediments and can persist for thousands of years, while lead, cadmium, and mercury from smelting and fossil fuel combustion have been measured in ice cores and sediment layers spanning millions of years. Even metamorphic and subduction processes can encapsulate chemical signatures within minerals, preserving evidence of surface processes over hundreds of millions of years. These indirect markers offer quantifiable methods to identify prior anthropogenic-like activity, complementing traditional fossil or structural evidence. The fossil record represents a partial and selective archive of life's history, reflecting only organisms and structures capable of long-term preservation. Fossilization, accessibility, and geological recycling create substantial biases which can obscure entire lineages or transient ecological communities. Quantitative models indicate that less than 0.1% of all species have been preserved as fossils, and ephemeral features, such as soft tissues or temporary constructions, are even less likely to survive. Chemical, isotopic, and sedimentary proxies, such as persistent heavy metals, industrial isotopes, or microplastics, provide alternative, measurable indicators of past surface activity. Combined with high-resolution stratigraphy and geochemical analysis, these data allow researchers to reconstruct environmental histories, population dynamics, and anthropogenic-like processes, even in the absence of conventional fossils, hidden civilizations in the deep time. If civilizations existed before humans, they would not be buried merely under soil or sediment, they would be entombed beneath epochs, erased by tectonic recycling, erosion, and deep-time geological processes. Plate tectonics alone subducts vast stretches of crust over tens to hundreds of millions of years. Entire continents have drifted thousands of kilometers since the Cambrian, carrying with them any structures, roads, or industrial debris that might have existed. Yet deep time, destructive as it is, also preserves in subtle ways. Ancient strata capture chemical, isotopic, and mineralogical records that scientists can read like the pages of a fragmented, partially burned book. Some of these pages contain anomalies that still puzzle researchers' whispers, however faint, of processes or events that defy conventional explanation and hint at extraordinary possibilities. In 2019, a collaborative study by MIT and the University of Southampton analysed South Atlantic Ocean sediment cores spanning roughly 56 million years ago, near the Paleocene-Eocene thermal maximum PET-M. The cores exhibited abrupt carbon isotope shifts, a global temperature rise of 5-8 degrees Celsius over a few thousand years, and widespread ocean anoxia, which significantly affected marine ecosystems. Carbon release during this interval is estimated at 3,000–7,000 gigatons, similar in magnitude to modern anthropogenic emissions. Most studies attribute the PET-M to massive volcanic activity in the North Atlantic igneous province, but the record shows a sharp carbon spike followed by long-term stabilization, providing a geochemical baseline for comparison with any potential industrial-scale emissions in Earth's past. Manganese nodules on the ocean floor grow at rates of 110 millimeters per million years, with some in the Pacific, Atlantic, and Indian Oceans reaching tens of millions of years in age. These nodules contain nickel, cobalt, copper, and rare earth elements, and NOAA mapping shows some isotopic compositions subtly differ from purely crustal sources. Although natural in origin, the longevity of these nodules illustrates that metals and minerals can retain cumulative chemical signals over deep time. Similar anomalies from industrial-scale processes could, in principle, be detectable if distinguished from volcanic or hydrothermal signatures through detailed geochemical analysis. Another striking example comes from Oklo in Gabon, Africa, where natural nuclear reactors operated about 1.7 billion years ago. Discovered in 1972, these uranium deposits underwent self-sustained fission reactions without any human intervention, producing isotopic anomalies of uranium-235 and rare fission products like neodymium-143. Oklo illustrates two critical points. First, geologically natural processes can mimic technologically induced isotopic signatures. And second, even a clear fission signal can survive billions of years if incorporated into stable minerals. For researchers searching for deep-time civilizations, Oklo serves as both a cautionary tale and a proof of concept technology, if it existed long ago, could leave detectable signatures in the mineral record, though their origin might be ambiguous. Paleontologist Peter Ward of the University of Washington has argued that intelligence is unlikely to be a one-time evolutionary event. Comparative neuroanatomy reveals multiple bursts of brain complexity. Cephalopods, birds, and certain reptiles developed disproportionately large brains relative to body size, separated by hundreds of millions of years. Octopuses, for example, demonstrate remarkable problem-solving abilities, tool use, and spatial learning, despite diverging from vertebrates over 500 million years ago. Similarly, avian lineages, particularly corvids and parrots, show sophisticated social learning and manipulation of objects. These examples suggest that the cognitive substrate for technological behavior is not unique to mammals. Over hundreds of millions of years, it is conceivable that one or more lineages reached a proto-technological stage, leaving only faint or indirect traces behind. Detecting past civilizations would require careful interpretation of geochemical anomalies. Late Cretaceous clay layers, for example, contain fine metallic particulates, soot, and mineral assemblages generally attributed to asteroid impacts or volcanic activity. While no anthropogenic sources have been confirmed, advances in high-precision isotope ratio mass spectrometry and synchrotron-based microimaging allow researchers to detect trace levels of synthetic or unusual isotopes, providing new analytical capabilities to investigate anomalous chemical signatures in ancient strata. Paleoclimatology uses trapped gases in ice cores, sediments, and carbonate minerals to reconstruct ancient atmospheric compositions. Compounds such as halocarbons, nitrogen oxides, and chlorofluorocarbons currently have no known natural analogues in the geologic record. Analytical methods now allow detection of extremely low concentrations or unusual isotopic ratios in mineral matrices, providing measurable proxies that persist far longer than physical structures or tools. To date, no pre-human anthropogenic traces have been identified, but these techniques expand the range of detectable geochemical anomalies. Other subtle geological markers include extraordinary sedimentary layering, anomalies in platinum group metals, and localized carbon black deposits. For example, Elevated iridium layers, famously associated with the KPG extinction, were initially linked to asteroid impact, yet some geochemists have pointed out that localized industrial combustion could produce similar profiles. Likewise, heavy metal enrichments in certain marine sediments might plausibly originate from extensive mining or smelting. The challenge lies in distinguishing natural processes from technological activity, a task complicated by the passage of hundreds of millions of years, during which erosion, subduction, and metamorphism continually recycle Earth's crust. As astrophysicist Adam Frank emphasized in a 2018 NASA publication, the absence of evidence is not evidence of absence. Earth's geological and biological filters are extraordinarily efficient at erasing transient activity. Even major human infrastructure might vanish almost entirely within 10–100 million years, leaving only scattered isotopic or chemical signatures. If civilizations did arise and vanish in deep time, their signals would be faint, fragmented, and easily misattributed to natural processes, but they are not necessarily undetectable. Plate tectonics, erosion, and geochemical cycling have destroyed most of Earth's surface record, yet measurable clues remain in the form of isotopic shifts, metallic nodules, fission signatures, and sedimentary anomalies. Each anomaly provides data for reconstructing ancient environmental and chemical histories. No pre-human civilizations have been confirmed, but sediment cores, isotopic measurements, and mineralogical analyses provide objective datasets for investigating chemical and geologic anomalies over deep time. What we'd expect to find today, if an ancient technological civilization ever existed, the traces it might leave behind would be subtle, scattered, and deeply hidden. Millions of years of erosion, tectonic upheaval, and biological decay act as relentless filters, erasing most physical evidence, yet not all signals vanish. To understand what might survive, we must examine persistence, which materials, isotopes, or chemical imprints can endure the immense timescales of deep time, and where these vestiges would be most likely preserved. Modern human activity deposits over 35 billion tons of anthropogenic material annually, including plastics, metals, concrete, and chemical byproducts. Many of these materials will persist over geologic timescales as technofossils, a term introduced by Jan Zalasiewicz and colleagues at the University of Leicester. Technofossils include corroded metal fragments, microplastics, and chemically altered sediment layers, providing measurable analogues for understanding the potential preservation of ancient industrial activity. Industrial processes produce measurable chemical fingerprints. Fossil fuel combustion alters carbon isotope ratios, delta, to the power of 13C in sediments, distinct from volcanic or natural carbon sources. Modern coal releases carbon with delta to the power of 13C values between 25 ALUs and 28 TERU, differing from atmospheric CO2 and carbonates. Small delta to the power of 13C deviations preserved in pelagic carbonates can indicate metabolic or chemical processes. Large-scale thermal emissions may also slightly affect oxygen isotopes delta to the power of 18O, producing shifts of 0.30 in well-preserved carbonate strata. Other chemical markers include sulfur, nitrogen, and heavy metals. Industrial metallurgy releases lead, cadmium, mercury, and zinc, each leaving subtle but persistent isotopic anomalies. Sedimentary lead can retain isotopic fingerprints for over 100 million years in stable rocks. Anthropogenic lead, such as that derived from smelting galena ores, has a distinct circumflex 206 petabytes, circumflex 207 petabytes ratio around 1.2, differing from natural volcanic or crustal sources, which tend to range from 1.18 to 1.25. Pre-human civilization mining or smelting ores could leave similar metallic traces in local or global sediment layers, particularly if large-scale metal production occurred over centuries. Certain metals and alloys are extraordinarily resistant to decay and virtually absent in natural geologic formations. Pure aluminum, titanium alloys, and rare earth metal composites do not occur naturally in significant quantities. Ancient civilizations using such metals would leave unusual mineralogical patterns detectable in cratonic regions, geologically stable continental shields, where rocks remain largely undisturbed for billions of years. The Yilgarn Craton in Western Australia, the Kapfau Craton in South Africa, and portions of the Canadian Shield are prime candidates. Sedimentary layers and intrusive rocks dating back 2-3 billion years may preserve geochemical anomalies indicative of ancient metallurgy, mining, or smelting activity. In these locations, even microgram-scale concentrations of aluminum or titanium within sedimentary laminations could provide lasting technofossil evidence. Modern plastics are particularly resistant to decay. Laboratory tests conducted by the Woods Hole Oceanographic Institution show that polyethylene and polyvinyl chloride may survive up to 500,000 years in marine sediments. Over tens of millions of years, such polymers could fossilize as carbon-rich films, inclusions within sedimentary rock or amorphous microplastic layers. Similarly, artificial dyes, resins, and composite materials might leave persistent chemical residues, potentially traceable with high-resolution Raman spectroscopy or Fourier transform infrared spectroscopy. Considering that humans have already produced over 8 billion tons of plastic in just the past 70 years, even a fraction fossilized in sedimentary rock would be measurable in parts per million, providing unmistakable technofossil evidence. Certain isotopes are unambiguous signatures of nuclear or industrial processes. Isotopes such as plutonium-244, uranium-236, and technetium-99 do not occur naturally in measurable quantities. Detection of these elements in ancient strata would constitute irrefutable evidence of artificial nuclear activity. The natural Oklo reactor demonstrates that fission signatures can persist for billions of years, but the distribution of isotopes there is distinct from anthropogenic patterns. Any anomalous fission products found outside natural reactors, especially localized enrichment of circumflex 236U to levels above 10 circumflex, 6 relative to circumflex 238U, would immediately suggest intelligent intervention. The chance of survival increases in geologically stable regions. Oceanic crust is largely recycled within 100 million years, making it unsuitable for preserving long-term traces. Continental shields, on the other hand, remain tectonically quiet over billions of years. Drilling programs such as the Canadian Lithoprobe and the South African Kalahari Borehole Project access rock layers up to 3 billion years old, providing pristine windows into ancient environmental conditions. Sedimentary basins in these regions may preserve subtle chemical anomalies, mineralogical oddities, or microfossil disruptions indicative of past industrial activity. Boreholes as deep as 5 kilometers already reveal layers dating from the Archean to the Proterozoic, demonstrating the preservation potential of stable cratons. Deep-sea sediments offer complementary archives. The Integrated Ocean Drilling Program IODP has recovered over 350,000 meters of cores globally, containing detailed chronological records of microfossils, isotopes, and mineral compositions. Even minor industrial events would alter sediment chemistry, oxygen isotopes, trace metals, or carbon ratios detectable with modern instruments. For example, a sudden spike in nickel or vanadium concentrations above 50 parts per million in pelagic clays could indicate extensive mining or combustion activity, while associated carbon anomalies might signal widespread fossil fuel use. Despite decades of exploration, no synthetic compounds or artificial isotopes older than the Holocene have been identified. As Dr. Gavin Schmidt of NASA emphasizes the geological record is patchy and more than 70% of Earth's crust lies beneath oceans, largely unmapped. Many potential sites of preservation may be buried under kilometers of sediment, metamorphosed into crystalline rock, or otherwise concealed from direct observation. Ancient ruins, if they existed, might now be scattered fragments within deeply altered strata, invisible without careful chemical, isotopic, or mineralogical analysis. Preserved traces are likely to be subtle, such as small chemical anomalies, isotope ratio deviations, unusual metal clusters, or localized thermal alteration zones. Modern cities, dams, mines, and industrial complexes will leave fingerprints for millions of years, but only in combination with chemical, isotopic, or mineralogical evidence can they endure the test of deep time. If humans vanished tomorrow, in 100 million years, all that might remain would be scattered technofossils, microplastic inclusions, and isotopic quirks embedded in sedimentary basins, a pattern likely mirrored by any ancient civilization that came before us. The geological blueprint of civilization. Humanity is leaving the most geologically conspicuous mark of any species in the planet's history, and in doing so, we are providing a blueprint for identifying what ancient technological civilizations might have left behind. Understanding the longevity, detectability, and transformation of our own technosphere offers a roadmap for what to look for in the deep time record. Concrete alone, a human-made rock, is estimated at 30 trillion tons, surpassing the total biomass of all living plants on Earth. Nature, 2020. This immense material dominates the lithosphere in urbanized regions and has already begun to fossilize in sedimentary layers through weathering, diagenesis, and mineral replacement. Metals such as iron, copper, and aluminum, extracted and refined over centuries, have been dispersed in quantities unprecedented in natural geological history. The U.S. Geological Survey, USGS 2022, reported that over 1.5 billion tons of steel and iron alone are produced annually, with concentrations in industrial zones exceeding local natural abundances by factors of 10-100. Glass, ceramics, and plastics infiltrate soils, rivers, and oceans globally, creating an almost indestructible technofossil record. Plastics have proven particularly persistent. By 2024, the United Nations Environment Programme reported that humanity generates over 400 million tons of plastic waste annually. Microplastics are now detected in Antarctic snow, the Mariana Trench, and even in the air over remote deserts. Laboratory studies show that polyethylene microfibers can survive for at least 500,000 years in marine sediments, while other polymers can resist degradation under pressure and heat, gradually converting into chemically stable forms that may mimic natural carbonaceous films. If a civilization millions of years ago had developed similar synthetic polymers, they could remain trapped in sedimentary strata as fossil plastics, indistinguishable from minerals unless examined with modern spectroscopy, Raman imaging, or mass spectrometry. Our atmosphere carries a permanent signature of human activity. Carbon dioxide levels have surpassed 420 parts per million, the highest in at least 3 million years. The isotopic composition of this CO2 reveals its anthropogenic origin, with delta to the power of 13 C values around 28 peri, consistent with fossil fuel combustion. Historically, the last time Earth experienced comparable CO2 concentrations was the Pliocene epoch, approximately 3-5 million years ago, when global mean temperatures were 2-3 degrees Celsius higher and sea levels 15-25 meters above present. This isotopic anomaly is now embedded in modern ice cores, ocean sediments, and peat bogs, where it will persist for millions of years. A pre-human civilization with large-scale energy use could have left similar atmospheric isotopic markers, detectable long after surface features vanished. Humanity's nuclear age has created yet another geological signature. Fallout from Cold War testing between 1952 and 1963 forms a global layer, now referred to as the Golden Spike for the Anthropocene. This layer contains detectable amounts of plutonium-239, cesium-137, and strontium-90, each of which persists for thousands to millions of years. While natural nuclear fission events are extremely rare, the presence of these isotopes in stratified layers is unmistakably artificial. Modern mass spectrometry can detect plutonium-239 at concentrations as low as 10 to the power of -14 grams per gram of sediment, allowing clear differentiation between natural and anthropogenic fission products. Agricultural activity has also rewritten the planet's biogeochemistry. The Haber-Bosch process has doubled the global pool of biologically available nitrogen, producing roughly 120 million tons of reactive nitrogen annually. Nitrogen isotopes in soils and sediments reveal this anthropogenic enrichment distinct from natural cycling. Fossilized soils, or paleosols, showing comparable nitrogen isotope anomalies, could signal ancient large-scale cultivation or fertilization. In modern studies, delta to the power of 15N enrichment in paleosols exceeding 5 area above background values correlates with high-intensity fertilizer use, providing quantifiable indicators of anthropogenic soil modification. Our technological reach extends into space, leaving extraterrestrial signatures that may survive far longer than any terrestrial construct. Over 36,000 artificial objects, larger than 10 centimeters now, orbit Earth, from satellites to spent rocket stages. Collisions and natural decay will eventually deposit these metallic fragments on Earth's surface or in the deep ocean, where metals such as titanium, aluminum, and stainless steel alloys may persist for millions of years. Micrometeorite-sized particles derived from space debris, rich in platinum group elements, could be mistaken for natural extraterrestrial infall unless carefully analyzed. Titanium-aluminum alloys from deorbiting satellites have been recovered in ocean sediments at depths exceeding 5,000 meters, showing minimal corrosion over 50 years and demonstrating potential for long-term stratigraphic preservation. Mining and industrial waste constitute another long-lived footprint. Tailings, slag heaps, and refined metal residues create chemically distinct landscapes. For example, the Norilsk region in Russia contains ore processing waste with nickel concentrations exceeding 50,000 parts per million, while the Sudbury Basin in Canada holds nickel and copper tailings over 2 kilometers deep. Over geological timescales, these concentrated metal deposits may be misinterpreted as natural ore anomalies, unless cross-referenced with mineralogy and stratigraphy. Analysis of ore layers with nickel, copper, and cobalt concentrations above 10,000 parts per million, combined with anthropogenic slag textures, provides quantifiable criteria for identifying industrial processing rather than natural deposition. By systematically analyzing these anthropogenic patterns, scientists can reverse engineer the types of evidence a past civilization might leave. Key indicators include abrupt isotope shifts, unusual distributions of metals or synthetic compounds, and rapid climate-altering events, essentially fingerprints of industrial-scale transformation. Quantitative thresholds, such as metal anomalies exceeding local background by factors of 10-100 or microplastic abundances above 1,000 particles per kg of sediment, are measurable indicators of industrial-scale influence in stratigraphy. Understanding our own footprint highlights the resilience and detectability of certain materials, the longevity of isotopic anomalies, and the potential for technological activities to create permanent environmental markers. Our own trajectory approaches what economists and astrobiologists refer to as the Great Filter, a series of existential challenges that may prevent any intelligent species from persisting on planetary timescales. For instance, global industrial emissions have already caused a temperature increase of 1.2 degrees Celsius since pre-industrial times, triggering sea level rise, ice sheet destabilization, and biodiversity loss at rates not seen in 66 million years. Climate models project that by 2100, continued emissions at current rates could raise global temperatures by 3-4 degrees Celsius, causing sea level rise of up to 1 meter, with irreversible ice sheet loss on Greenland and parts of Antarctica over millennia. These processes will create globally stratigraphically identifiable carbon and isotopic anomalies in sediments, ice cores, and paleosols, providing measurable markers of industrial-scale activity. The spatial distribution of human activity affects techno-fossil density. Urban areas like Tokyo and New York concentrate millions of tons of concrete, steel, and plastics, while industrial zones, such as the Ruhr Valley, have metal concentrations 10-100 times above local baselines. Low-density regions, including the Australian outback, show soil plastic concentrations below 50 milligrams per kilogram. Stable cratons, like the Canadian Shield, preserve thick sedimentary sequences where slag layers, microplastic-rich soils, and industrial residues can persist for millions of years, whereas tectonically active regions experience rapid erosion and subduction. The study of humanity's geological imprint catalogues measurable materials, isotopes, and environmental markers that persist through deep time. Plastics, metals, nuclear isotopes, synthetic compounds, and engineered landscapes transform over millennia, leaving stratigraphic anomalies detectable in sediment cores, paleosols, and ice layers. For instance, industrial metals in soils and tailings exceed local natural abundances by factors of 10-100, and microplastic concentrations in marine sediments range from 10 cubed to 10 to the power of 6 particles per kilogram. These data provide reference points for identifying unusual sedimentary patterns in older strata. Concrete, microplastics, and spikes in delta to the power of 13C or delta to the power of 15N provide measurable markers in sedimentary and ice core records. Radionuclides such as plutonium-239 and cesium-137, deposited during Cold War testing, remain detectable for thousands of years. Engineered materials, including concrete, ceramics, and industrial glass, exhibit chemical signatures like elevated boron and lithium absent in natural deposits. Quantifying these markers allows stratigraphers and geochemists to trace the persistence of human influence through geological timescales. Global datasets on radionuclides, synthetic compounds, and metals now allow precise mapping of anthropogenic deposits. Radionuclide layers appear consistently across continents, while microplastic densities vary between populated deltas and polar regions. Engineered metals such as titanium and aluminum from orbital debris are detectable in sediments. These measurable distributions provide a framework for identifying anomalous layers in the geological record that may correspond to large-scale industrial or technological activity. Human imprints in the rock record. The Great Filter hypothesis proposes that intelligent civilizations rarely survive long enough to achieve interstellar presence. Most species capable of technological sophistication appear to fail at some stage, often coinciding with large-scale manipulation of their environment. Current human activity, industrialization, energy use, and global environmental impact represents a measurable instance of this stage. Robin Hanson first formalized the Great Filter concept in 1996, identifying potential points of failure ranging from the emergence of life itself to self-destruction through technology. For Earth, the most imminent risks are environmental collapse, nuclear or radiological warfare, unchecked biotechnological manipulation, and destabilizing artificial intelligence. Modeling studies indicate that extreme environmental disruption could lead to multi-millennial impacts on global biodiversity and ecosystem stability. History, both on Earth and across the cosmos as inferred from exoplanetary studies, suggests that environmental feedback loops can spiral beyond recovery. The Permian-Triassic mass extinction, approximately 252 million years ago, illustrates this vividly. Global temperatures rose by as much as 10 degrees Celsius, ocean acidity increased sharply, and atmospheric oxygen dropped by an estimated 12%. Roughly 96% of marine species and 70% of terrestrial vertebrates vanished. Benton and Twitchett, 2003. Volcanism in the Siberian traps, methane release from gas hydrates, and positive carbon cycle feedback contributed to an unprecedented collapse of ecological stability. Modern human activity mirrors several aspects of this process. Fossil fuel combustion has elevated CO2 from pre-industrial levels of 280 parts per million to over 420 parts per million in 2023, while methane emissions from thawing permafrost and livestock exceed 570 million tons annually based on NOAA 2023. Deforestation and habitat loss, which remove roughly 10 million hectares of forest per year, further accelerate climate feedback. If civilization were to collapse abruptly, the geological footprint would resemble ancient extinction events. Ice cores, peat deposits, and sedimentary strata would capture sharp spikes in carbon isotopes, sudden declines in biodiversity, and layers indicating soil erosion or reforestation. Over millions of years, artificial components, plastics, concrete, alloys, and radionuclides would become chemically altered or buried, leaving subtle anomalies in isotope ratios, mineral assemblages, or microplastics trapped in sedimentary rock. Paleoclimatologists studying the Paleocene-Eocene thermal maximum PET-M observe rapid carbon input, warming, and biotic turnover, demonstrating that geochemical signals from abrupt events can be difficult to distinguish from overlapping natural processes. Rapid environmental disruption from technological activity leaves faint but measurable traces, chemical fingerprints, mineralogical anomalies, and isotopic shifts before ecosystems recover. On Earth, repeated episodes of industrial pollution over centuries have created layers detectable in sediments and ice cores, demonstrating how technological activity can persist in the geological record. Astrobiologists, including Dr. Charles Lineweaver at the Australian National University, argue that the most probable great filter for Earth-like planets is self-inflicted rather than cosmic. Statistically, global sterilization from asteroid impacts, supernovae, or gamma-ray bursts is rare, occurring perhaps once every few hundred million years. In contrast, ecological collapse driven by industrial-scale activity could occur on any habitable planet with a technological species. Planetary modeling studies by Adrian Lenardic suggest that even modest increases in greenhouse gas emissions can initiate non-linear climate feedbacks, accelerating ice sheet disintegration, altering ocean circulation, and triggering mass extinction cascades within centuries to millennia. Current projections indicate rising risks. The IPCC's Sixth Assessment Report in 2023 projects that if emissions continue at present rates, global mean temperatures could exceed 2.5 degrees Celsius above pre-industrial levels by 2100. This warming is expected to accelerate ice melt in Greenland and Antarctica, release hundreds of gigatons of methane from permafrost, and destabilize terrestrial and marine ecosystems. Geochemical records would capture carbon isotope shifts, nitrogen cycle perturbations, and anomalous metal concentrations from industrial runoff, which over millions of years could resemble natural extreme events unless analysed in detail. From a geological perspective, the collapse of an industrial-scale civilization becomes increasingly difficult to distinguish from natural climate or biotic events after several million years. During ecosystem recovery, artificial signals degrade, leaving isotopic and mineralogical anomalies. Patterns such as abrupt carbon excursions, sudden species turnover, and geochemical enrichment can be misinterpreted as natural phenomena in sedimentary strata. Scientific understanding allows quantification of climate feedbacks, modelling of nuclear winter scenarios, and evaluation of artificial intelligence risks. Effective mitigation depends on coordinated global action. Historical examples, including the collapse of the Roman Empire and the Dust Bowl of the 1930 seconds, demonstrate that moderate environmental or societal stresses can overwhelm complex societies. Scaling these dynamics to a planetary civilization introduces additional uncertainty in ecosystem and population stability. Furthermore, the spatial distribution of industrial activity affects detectability in the geological record. Urban centers, mining regions, and industrial zones concentrate technofossils, radionuclides, and isotopic anomalies, while rural or minimally inhabited areas contribute little. For ancient civilizations, failure in a concentrated technological hub might leave traces only in localized strata, whereas global industrialization, as with humanity, maximizes preservation potential. This implies that even if multiple civilizations collapsed, the surviving geological record may be uneven, with anomalies scattered and subtle. The Great Filter concept provides a framework for interpreting planetary systems. Self-induced environmental disruption may prevent long-term persistence of intelligent species. Exoplanetary observations such as elevated greenhouse gas concentrations, unusual metallic reflectivity, or isotopic anomalies can indicate extreme planetary modification, analogous to patterns produced by industrial activity on Earth. Rapid energy use, chemical alteration, and resource overexploitation create geochemical signals detectable over geologic timescales. Geological records demonstrate that abrupt environmental change can lead to the extinction of complex species. Modeling studies and historical examples allow identification of risk thresholds and potential mitigation strategies. Analysis of isotopic, geochemical, and sedimentary anomalies provides a basis to evaluate whether ancient industrial activity could have produced detectable traces. Patterns of environmental collapse in Earth's history illustrate how species are affected by rapid ecological perturbations. In this context, the Great Filter serves as both a theoretical and practical lens. It bridges deep-time geological patterns with contemporary environmental crises, providing insight into why technofossil evidence may be scarce, dispersed, or subtle. Studying abrupt climate events, isotopic excursions, and mass extinction horizons allows scientists to distinguish between natural planetary dynamics and potential anthropogenic or pre-human technological influences. By doing so, we gain not only the ability to search for ancient civilizations, but also the insight necessary to avoid becoming a cautionary tale ourselves. Human industrial, environmental, and technological activities interact with geological and planetary processes, producing measurable changes in atmospheric composition, sediment deposition, and ecosystem dynamics. Continued monitoring of greenhouse gas emissions, land use, and resource exploitation provides data on the potential long-term impacts of these activities on Earth systems. Patterns of geochemical and sedimentary change serve as a record of anthropogenic influence, which can inform models of planetary stability and the detectability of prior technological activity in the geological record. Natural processes can act as planetary filters, erasing ecosystems, reshaping geochemistry, and altering the preservation of evidence from species. Cosmic impacts, supervolcanic eruptions, and planetary-scale glaciations have historically caused mass extinctions and global environmental change, affecting biodiversity and the sedimentary record. These events can obscure or modify geochemical and fossil evidence, complicating the detection of prior industrial or technologically active species. Natural filters, cosmic and planetary threats. Not all great filters originate within civilizations. Some arise from cosmic or planetary events so massive and sudden that technological mitigation would be limited. Geological evidence shows that Earth has repeatedly experienced cosmic impacts, supervolcanic eruptions, and other hazards that disrupted ecosystems and reset evolutionary trajectories. Asteroid impacts are perhaps the most familiar of these threats. Earth's surface is pockmarked with evidence. Over 190 confirmed impact craters have been catalogued by the Planetary and Space Science Center, with countless smaller craters yet undiscovered or eroded. The Chicxulub impact, 66 million years ago, famously ended the reign of the dinosaurs, but the Vredefort crater in South Africa dwarfs it, spanning 300 kilometers and created by an asteroid estimated at 15 kilometers across. The energy released would have been over 10,000 times the combined yield of all nuclear weapons ever built, vaporizing rock, triggering wildfires across continents, and injecting massive quantities of dust and aerosols into the atmosphere. Even today, scientists modeling asteroid impacts note that a strike only 1-2 kilometers in diameter could cause global agricultural collapse and severe climate disruption, placing any civilization at immediate existential risk. NASA's Center for Near-Earth Object Studies, CNEOs, tracks over 32,000 asteroids near Earth, with dozens discovered each week. Long-term modeling predicts that impacts capable of causing civilization-level destruction occur roughly once every 100 million years. The timing of several mass extinctions coincides with these intervals, suggesting a potential causal link. Even smaller strikes, while not globally lethal, can inject large amounts of sulfur and dust into the stratosphere, triggering impact winters that cool the planet by several degrees and disrupt food chains for decades. Volcanism on a planetary scale poses another existential threat. Supervolcano eruptions can alter climate and atmospheric chemistry for centuries. The Toba eruption in Sumatra, roughly 74,000 years ago, expelled more than 2,800 cubic kilometers of ash. Genetic evidence suggests that this may have reduced Homo sapiens to as few as 10,000 breeding pairs globally, creating a severe population bottleneck. Even more catastrophic were the Siberian Traps eruptions, which lasted nearly 1 million years and contributed to the Permian-Triassic extinction 252 million years ago. These flood basalts released unprecedented amounts of carbon dioxide and sulfur dioxide, driving runaway greenhouse warming, ocean acidification, and a collapse of marine and terrestrial ecosystems. Modern planetary modeling indicates that a similar eruption today would devastate global food systems, disrupt atmospheric circulation, and produce multi-decadal cooling or warming episodes depending on sulfur to carbon ratios. Cosmic radiation events are rarer but potentially more lethal. Gamma-ray bursts, GRBs, emitted during the collapse of massive stars, release energy equivalent to 1 billion nuclear bombs within seconds. Adrian Melott and Brian Thomas in 2014 proposed that a GRB could have triggered the Ordovician-Silurian extinction 443 million years ago by stripping away the ozone layer, exposing surface ecosystems to lethal ultraviolet radiation. Such events occur roughly once every 500 million years in our galaxy, yet their effects are catastrophic for life on any planet within thousands of light years. Supernovae, particularly Type II explosions, can also irradiate planets, disrupting DNA integrity and atmospheric chemistry. Closer to home, the Sun is a dynamic source of variability. Long-term solar evolution indicates that, within 1 billion years, increasing luminosity will trigger a runaway greenhouse effect, boiling Earth's oceans and sterilizing the planet. Short-term variations also matter. Historical solar minima, such as the Maunder minimum from 1645, 1715, caused the Little Ice Age, demonstrating that even small shifts in solar output can disrupt climate, agriculture, and societal stability. Modern climate models incorporate solar irradiance fluctuations, volcanic aerosols, and greenhouse gas forcing to estimate planetary habitability windows. Earth's orbital and axial cycles influence climate variability. Milankovitch cycles variations in eccentricity, axial tilt, and precession drive ice ages and interglacial periods over tens to hundreds of thousands of years. The Pleistocene epoch experienced repeated glaciations, each lasting 80,000, 120,000 years, periodically restricting habitable regions and affecting migrations and population sizes in humans and megafauna. Asteroid impacts, supervolcanism, cosmic radiation, solar evolution, and orbital cycles have repeatedly caused large-scale ecological disruption. Geological and fossil records show that such events significantly reduced biodiversity and altered ecosystem structures. These filters are universal in principle. Any planet orbiting a star may experience comparable stochastic hazards. The Chicxulub impact released an estimated 100 million megatons of TNT equivalent, while the Toba eruption expelled 2,800 cubic kilometers of pyroclastic material. GRBs emit energy equivalent to roughly 10 to the power of 46 joules. Even a solar superflare, which may occur once every few thousand years, could disrupt electrical grids, satellites, and climate-sensitive agriculture globally. These energy scales indicate that natural events can produce environmental changes far beyond typical human activity levels. Natural hazards can obscure evidence of prior civilizations. Sediment deposited after asteroid impacts, flood basalts, or glacial episodes can bury materials or chemically alter them, leaving only subtle isotopic or mineralogical anomalies. Durable materials such as metals, ceramics, or synthetics may be scattered, corroded, or geologically reworked beyond recognition, complicating detection in the fossil record. Fossil evidence shows that biodiversity rebounds after mass extinction events. For example, the Ordovician, Permian, and Cretaceous extinctions were followed by radiations of new species, often surpassing previous diversity levels. These patterns illustrate the resilience of life despite repeated environmental catastrophes. Collectively, asteroid impacts, supervolcanism, cosmic radiation, solar evolution, and orbital cycles constitute natural great filters, repeatedly driving large-scale ecological and evolutionary changes. Geological and fossil records provide evidence of these processes through abrupt changes in species abundance, isotopic excursions, sediment deposition, and other geochemical signatures. The timeline of civilizational rise and fall. Earth's history shows cycles of destruction, renewal, extinction, and evolution. Fossil and geological records indicate that life repeatedly surges, collapses, and adapts over billions of years. Complex cognition has arisen in multiple lineages, as suggested by evidence of advanced problem-solving in cephalopods, corvids, and primates, although no direct evidence of technological civilizations exists prior to humans. Each period of potential intelligence is short relative to geological time and unlikely to leave durable surface traces. To visualize the timeline, consider compressing Earth's history into a single calendar year. In this model, Earth forms on January 1st. Life emerges by late February. Multicellular organisms appear in November. The dinosaurs dominate from December 13th to 26th, and humans arrive at 11:52 p.m. on December 31st. Each mass extinction, the Ordovician-Silurian 444 million years ago, Late Devonian 372-359 million years ago, Permian-Triassic 252 million years ago, Triassic, Jurassic 201 million years ago, and Cretaceous-Paleogene 66 million years ago would occupy brief hours or minutes in this compressed year, erasing previous dominances and opening ecological niches for new forms of life. The Cambrian explosion, beginning around 541 million years ago, represents the first major surge of biological complexity. Within roughly 20 million years, almost all modern animal phyla appeared. Evolution then entered a pattern of slow development, punctuated by rapid, catastrophic resets. After each collapse, dominant lineages shifted. Jawed fish rose in the Devonian, reptiles in the Permian, dinosaurs in the Mesozoic, and mammals in the Cenozoic. Each transition reflects not just survival, but the opportunistic filling of vacated ecological roles, suggesting that evolutionary success is as much about timing and contingency as inherent traits. Intelligence is not guaranteed, yet convergent evolution hints that complex cognition arises repeatedly under the right circumstances. Cephalopods, corvids, cetaceans, and primates independently developed sophisticated problem-solving, communication, and tool use. Simon Conway Morris of Cambridge University argues that evolution frequently rediscovers intelligence, implying that Earth could have fostered multiple intelligent species long before humans appeared. Even social insects exhibit distributed problem-solving on a colony-wide scale, hinting at alternative architectures of intelligence that may leave subtle traces but no permanent technosignatures. Considering the last 600 million years of complex life, even a modest estimate of 100,000 years per technological civilization allows for 6,000 sequential windows for civilizations to rise and fall. In geological terms, these are brief instants. Erosion, subduction, metamorphism, and sedimentation would erase surface artifacts long before a new civilization could appear. Only indirect signatures, isotopic anomalies, shifts in sedimentary chemistry, or unusual mineral ratios might remain detectable. Erosion, subduction, metamorphism, and sedimentation can erase surface artifacts, leaving only indirect signatures such as isotopic anomalies, shifts in sedimentary chemistry, or unusual mineral ratios detectable in the geological record. The Carboniferous period, 359-299 million years ago, exemplifies a time when intelligence could plausibly have emerged. Oxygen levels peaked at 35% compared to today's 21%, supporting giant arthropods like Meganeura, amphibians, and early amniotes. Extensive coal swamps, freshwater systems, and complex terrestrial habitats created opportunities for intricate social behaviors. Fossilized trackways reveal evidence of group coordination, predator-prey strategies, and possibly even ritualized behavior. While there is no direct evidence of technological activity, ecological richness and brain-to-body ratios in some lineages suggest a window in which intelligence could plausibly arise only to be reset by the Permian-Triassic extinction, which eradicated over 90% of species. Population modeling of hypothetical civilizations highlights the temporal fragility of intelligence. Even a 100,000-year-long civilization represents only 0.017% of the Carboniferous to Permian interval. Surface evidence, unless continuously maintained, would vanish beneath tectonic recycling or burial in sediment. Deep core analysis, however, could reveal unusual carbon isotope ratios, abrupt mineral compositions, or anthropogenic elements, signatures that might hint at prior industrial activity without leaving a recognizable technological artifact. Astrobiologist David Grinspoon emphasizes that Earth may be a serial experimenter in intelligence. Each mass extinction, whether caused by volcanism, asteroid impact, or climate instability, resets ecological landscapes, allowing new evolutionary experiments. Intelligence, in this view, is not a permanent outcome, but a recurring transient state, emerging when conditions favor problem-solving, social cooperation, and resource manipulation, only to be extinguished by forces beyond the species' control. Evidence from the fossil record supports the idea of repeated experimentation. After each extinction, biodiversity rebounds, often exceeding previous levels. The Ordovician radiation produced thousands of new marine species, while post-Permian recovery took several million years, but eventually enabled the dominance of archosaurs and early mammals. Each recovery phase is accompanied by rapid evolutionary innovation, demonstrating resilience and adaptability, but not necessarily permanence. If intelligent species appeared in these windows, they may have risen and fallen without leaving a detectable trace. Geochemical evidence offers tantalizing clues. Studies of carbon isotopes, particularly delta to the power of 13C anomalies, reveal abrupt shifts in atmospheric composition during extinction events. Unexplained spikes in trace metals, rare isotopes, or synthetic compounds within ancient sediments could represent signatures of previous industrial activity. While no definitive technosignatures have been confirmed, the possibility remains that subtle chemical fingerprints persist in the geological record, awaiting discovery. The Great Filter concept incorporates external hazards, asteroid impacts, gamma-ray bursts, and supervolcanism, alongside internal risks such as climate instability and technological collapse. Geological evidence indicates that multiple extinction events have periodically reduced biodiversity, showing that survival depends on environmental stability and ecological resilience. Mass extinctions and climate shifts act as resets in Earth's biosphere, repeatedly reorganizing ecosystems and allowing new lineages to dominate. Fossil and geochemical records show that life can rapidly diversify following these events, occasionally producing complex traits, but leaving ambiguous evidence of prior intelligence. Deep time cycles illustrate the transient nature of complex traits and ecosystems. Fossil and isotopic records show repeated recoveries and collapses, highlighting the sensitivity of life to both internal and external environmental pressures over geological timescales. Researchers search for past civilizations by analyzing geological, isotopic, and mineralogical anomalies that could survive extinction events. Such studies investigate whether chemical or mineral signatures exist that indicate prior, unusual technological activity. Earth's timeline shows that complex traits and potential intelligence have emerged multiple times but may be ephemeral. Fossil and geochemical records indicate gaps in the historical record, where complex lineages appeared and disappeared, leaving limited or ambiguous evidence of prior advanced activity. Searching the rocks for ghosts. The hunt for ancient civilizations is not an excavation of ruins, but an investigation of chemistry, mineralogy, and isotopic subtlety. Modern geoscience equips researchers with tools to detect subtle chemical and structural anomalies in Earth's history. Electron microscopes can resolve nanometer-scale structures, while deep-core drills reach kilometers beneath the surface, allowing detailed analysis of ancient rocks and sediments. One primary avenue involves isotopic analysis. Industrial or technological activity often leaves distinctive signatures in stable isotopes, particularly carbon and nitrogen. Human-driven fossil fuel combustion has caused a measurable 1.5 E1 depletion in 1O-pub-C since the Industrial Revolution. If a similar anomaly were found in pre-human strata, absent volcanic eruptions, microbial shifts, or organic decay, it could indicate deliberate chemical manipulation. Nitrogen isotopes offer complementary insights. The Haber-Bosch process, for example, produces highly enriched 1 ratios in fertilizers. Ancient analogues might reveal similar large-scale biochemical engineering by unknown agents. Trace metals form another promising line of evidence. Mining and metallurgy redistribute elements such as copper, nickel, and rare earth metals in concentrations far beyond natural baselines. In 2020, researchers at ETH Zurich mapped global metal anomalies in sediment cores, confirming that industrial activity has produced a detectable geological footprint in just a single century. Detecting similar patterns in older sedimentary sequences, such as the Proterozoic or late Paleozoic, could suggest systematic extraction or smelting. These analyses rely on inductively coupled plasma mass spectrometry, ICP-MS, and synchrotron radiation techniques capable of measuring parts per billion or even trillion. The study of sedimentary plastics, though nascent, is scientifically promising. Plastiglomerates hybrid rock-plastic composites, identified by the University of Plymouth along modern coastlines, form mineralized structures. These materials combine molten plastic, sand, and volcanic or basaltic fragments, and may persist for millions of years under sedimentary pressure. Long-lived synthetic polymers in ancient deposits would provide evidence of persistent synthetic materials. Nuclear isotopes provide perhaps the most unambiguous markers. Plutonium-244, with an 80 million year half-life, would persist over hundreds of millions of years, allowing detection of civilizations employing nuclear technology in deep time. Similarly, unusual concentrations of technetium or americium, if found outside known natural decay chains, could signify prior fission reactors. So far, no evidence exists outside human-era deposits, but sampling is limited. Subglacial cores in Greenland and Antarctica, abyssal plain sediments, and cratonic basement rocks remain largely unexplored. Each new core adds tens of millions of years of environmental history to the search space. The International Ocean Discovery Program, IODP, exemplifies the potential of this work. With over 400 kilometers of drilled cores spanning every major ocean basin, the program provides continuous climate and geochemical records extending tens of millions of years. Advanced spectroscopic scanning and X-ray fluorescence analyses allow detection of synthetic polymers, halocarbons, or isotopic anomalies at concentrations of parts per trillion. Such precision transforms the search for ancient civilizations into a statistical and chemical enterprise, rather than a purely morphological or archaeological one. Remote sensing offers complementary insights. NASA's GRACE and SWAT missions map gravitational anomalies and subsurface topography beneath ocean sediments. Some patterns, linear ridges, rectilinear depressions, and clustered mounds are almost certainly geological, yet they reveal the potential for detecting organized, artificial structures even when obscured by kilometers of sediment. As computational imaging and machine learning advance, distinguishing between natural geomorphology and potential technogenic formations becomes increasingly feasible. Organic geochemistry also plays a growing role. Polycyclic aromatic hydrocarbons PAHs, persistent halogenated compounds, and synthetic organophosphates could survive in sedimentary matrices for tens of millions of years. When combined with isotopic signatures, these compounds offer a multi-layered record of technological processes. Scientists have begun experimenting with high-pressure pyrolysis and Fourier transform infrared spectroscopy to detect these faint traces in ancient shales and siltstones. Despite these tools, no unusual pre-human technological signatures have been discovered. Dr. Adam Frank of the University of Rochester emphasizes that the absence of such evidence clarifies what geochemical and isotopic patterns scientists should focus on. Earth's sedimentary record functions as a detailed archive of environmental perturbations and biological transformations. Future work increasingly focuses on extreme environments. Subglacial lakes in Antarctica, such as Lake Vostok and Lake Wields, harbour sediments undisturbed for tens of millions of years. Similarly, abyssal trenches and cratonic shield regions, like the Pilbara in Australia or the Karpfeil in South Africa, preserve ancient lithologies relatively resistant to tectonic recycling. Cores from these locations could reveal isotopic or metallic anomalies long erased elsewhere, offering glimpses into deep-time industrial activity. Earth's geological record is a layered chemical archive documenting environmental and biological changes over billions of years. Subtle chemical and isotopic anomalies in sediment layers provide measurable information about past processes, although no evidence of pre-human technological activity has been identified. In all cases, the challenge is distinguishing extraordinary signatures from extraordinary natural processes. Volcanism, hydrothermal alteration, and massive organic deposition can mimic some isotopic and mineral anomalies. Rigorous modeling, cross-validation, and multi-proxy approaches are essential to avoid false positives. The field requires integration across geochemistry, planetary science, archaeology, and evolutionary biology. It is a transdisciplinary effort to read Earth's memory for the faintest echoes of intelligence. The search for deep-time civilizations reframes humanity's relationship with the planet. Earth is not a static backdrop, but a layered chemical archive recording environmental experiments across billions of years. If intelligence arose before, it may have left no trace beyond subtle chemical imbalances, yet these fingerprints remain detectable in principle. Each discovery, or lack thereof, informs both our understanding of Earth's history and the rarity or fragility of technological life in the universe. The search for chemical and isotopic anomalies continues in oceans, ice, deserts, and shield regions. Analysis of sediment cores, isotopic ratios, and trace metal concentrations can reveal unusual geological or chemical processes. Improved techniques also support the application of these methods in planetary exploration to detect chemical anomalies on Mars, Europa, and Enceladus. Deep-time experiments. Are we the survivors? What if humanity isn't Earth's first civilization, but the first to survive? This possibility reframes the question of intelligence entirely. Instead of focusing solely on lost predecessors, we might consider ourselves inheritors of deep-time experiments in cognition, technology, and societal organization. The Earth, in this view, is a palimpsest. Layers of biological and ecological experiments, each one building upon the failures of the past. Evolution demonstrates a remarkable ability to reuse successful designs. Anatomical, behavioral, and cognitive traits rarely emerge de novo. They accumulate over millions of years of adaptation. The human neocortex, which underlies abstract reasoning, planning, and self-awareness, evolved from primitive cortical structures present in early mammals over 200 million years ago. Cetaceans, elephants, corvids, and cephalopods have independently developed advanced intelligence using alternative neural architectures. Octopuses, for instance, demonstrate spatial memory and problem-solving with a distributed nervous system, while corvids exhibit causal reasoning and episodic-like memory. This convergence suggests intelligence is a recurring evolutionary outcome rather than a singular fluke. If previous civilizations existed, their extinction could have opened ecological niches for successive intelligent lineages. The Cretaceous-Paleogene extinction 66 million years ago wiped out the non-avian dinosaurs, but within 10 million years, mammals diversified explosively, filling every terrestrial niche. Some, like the multituberculates and early primates, evolved arboreal lifestyles, tool manipulation, and social complexity, indicating that ecosystems rapidly reorganize to accommodate new forms of intelligence. These cycles of destruction and renewal hint that intelligence may not be linear. It is punctuated by ecological resets that create opportunities for repeated emergence. Anthropologists studying evolutionary bottlenecks suggest that crises can paradoxically refine intelligence. The Toba supervolcano eruption 74,000 years ago reduced human populations to possibly as few as 3,000, 10,000 individuals. Genetic evidence from the Human Genome Diversity Project confirms a sharp reduction in diversity, consistent with a population bottleneck. Yet this period also coincides with a cultural leap. The earliest confirmed art, beads, and symbolic artifacts appear, suggesting that environmental stress can catalyze complex social cognition. By analogy, deep time extinctions may have forged repeated bursts of technological or cultural development among unknown predecessors. Fossil and paleoneurological studies indicate that hominin lineages have shown expansion of the prefrontal cortex and Broca's area over the last 2.5 million years, consistent with the gradual development of complex cognition. Tool use, social organization, and environmental manipulation evolved progressively in these lineages, contributing to the emergence of Homo sapiens. David Grinspoon's continuity hypothesis proposes that evolutionary processes may lead to recurring phases of complex behavior and ecological impact. Residues from earlier biological events, such as genetic adaptations or ecosystem modifications, can influence subsequent evolutionary trajectories. Human evolution reflects the cumulative effects of these deep-time ecological and genetic processes. Energy consumption, environmental modification, and global communication are measurable characteristics of technological societies. Human impacts, such as increased atmospheric CO2, nitrogen cycle disruption, and biodiversity changes, represent detectable planetary signatures. The Anthropocene can be studied through geochemical, isotopic, and ecological measurements that quantify these effects. The concept of the Great Filter in astrobiology refers to a set of probabilistic barriers that may limit the emergence or survival of technological civilizations. Ecological pressures, resource constraints, and technological risks are measurable factors that influence the longevity of complex societies. Human use of environmental monitoring and predictive modeling allows assessment of these risks. This scenario also raises subtle questions about inheritance. Could aspects of intelligence be reinforced across successive evolutionary experiments? Some evolutionary biologists propose that cultural and behavioral memory can persist beyond single lineages. For example, primate tool traditions, transmitted across generations, influence problem-solving ability and social organization. Analogously, if intelligence arose multiple times in Earth's deep history, ecological or chemical imprints might have indirectly guided subsequent cognitive evolution, creating a continuity that culminated in humans. Effective management of planetary systems requires energy efficiency, biodiversity conservation, and mitigation of technological risks. Chemical, isotopic, and ecological measurements inform strategies for climate adaptation, resource management, and environmental stability. Consider the possibility of recurrence beyond Earth. If intelligence is repeatedly favored by evolution, then other planets with Earth-like conditions might undergo similar cycles of rise and collapse. Understanding our own history as a survivor lineage provides a blueprint for evaluating exoplanetary technosignatures. Observations of atmospheric composition, surface chemistry, and isotopic ratios can provide indirect evidence of technological activity if it occurred. Such measurements, combined with models of planetary evolution, allow scientists to assess whether complex life or industrial processes could have temporarily altered a planet's environment. The presence of transient civilizations elsewhere could follow the same pattern. Brief, fragile bursts of technology erased by planetary or self-inflicted crises, leaving only chemical or isotopic residues detectable from afar. In practical terms, this perspective reframes humanity's mission. Our current moment is not just a culmination, but a critical junction. Maintaining civilization requires monitoring ecological indicators, modeling climate feedbacks, and applying sustainable technologies to stabilize and sustain complex societies. Awareness of potential predecessors' fates underscores the fragility of complex life, but also its adaptability. Civilizations may vanish, but intelligence can be tracked through measurable planetary signatures and preserved knowledge, and perhaps this time with self-conscious guardianship. Seen in this light, the future becomes a test of continuity. Surviving the Great Filter requires implementing evidence-based strategies in energy management, biodiversity conservation, and climate stabilization. Every choice, from renewable energy deployment to land use planning and pollution mitigation, interacts with the long-term evolution of intelligence on Earth. If we succeed, we may be the first civilization to endure while leaving measurable improvements in planetary systems, such as stabilized carbon cycles and preserved biodiversity. If we fail, we become another layer in the strata of vanished intelligence, detectable only through geochemical and isotopic anomalies. Edge of extinction, the challenge of survival. Humanity now stands at a crossroads unprecedented in its evolutionary history. For the first time, a single species wields the power to reshape the climate, alter genomes, manipulate entire ecosystems, and venture beyond its planetary cradle. Yet each of these capabilities carries latent danger. The very technologies that can secure our survival may also precipitate our collapse. Preparing for the next great filter requires more than ambition. It demands deliberate foresight, system-level planning, and humility in the face of planetary forces. Climate destabilization remains the most immediate and measurable risk. According to the Intergovernmental Panel on Climate Change, IPCC 2023, global mean surface temperatures are increasing at 0.2 degrees Celsius per decade, faster than any sustained warming event in the last 65 million years. The National Oceanic and Atmospheric Administration reported that 2024 was the hottest year on record, with an average global temperature 1.45 degrees Celsius above pre-industrial levels. Sea level rise has accelerated to 4.1 millimeters per year, threatening coastal megacities and agricultural zones. Ocean acidification, driven by increasing CO2 absorption, now stands at a pH of 8.05, a 26% increase in hydrogen ion concentration since the Industrial Revolution, endangering coral reefs, shellfish, and global fisheries that feed over 3 billion people. Energy grids in the United States and Europe experienced an average of 12% outages in 2023 due to climate-related events, and global food supply chains face disruptions that could impact over 600 million people by 2030. The Arctic is warming 3 times faster than the global average, with 3.3 million square kilometers of sea ice lost since 1979, exposing further feedback loops that accelerate warming. Energy transition is another central component of preparation. Humanity currently consumes roughly 620 exajoules annually, according to BP Statistical Review in 2024, with fossil fuels providing approximately 80% of that total. Global coal use alone accounts for 14 gigatons of CO2 emissions annually, while natural gas contributes an additional 7.5 gigatons. Energy-related disruptions cost the global economy approximately $650 billion annually, highlighting the urgency of transitioning to low-carbon energy sources. Shifting toward renewables, nuclear fusion, and advanced energy storage is therefore critical. Countries like Denmark, with 50% of electricity derived from wind, and France, with 70% from nuclear power, offer models for partial decoupling from carbon-intensive energy. But scaling these solutions globally presents unprecedented logistical and technological challenges. Battery technologies, such as lithium-ion and emerging solid-state designs, must increase in capacity by at least 400% by 2050 to meet projected demand for electrified transport and grid storage. Beyond Earth's atmosphere, cosmic hazards loom. The NASA DART mission in 2022 successfully altered the trajectory of asteroid Dimorphos by 0.4 mm per second, a proof of concept that humanity could, in principle, defend against Chicxulub-scale impacts. Yet there are over 25,000 known near-Earth objects larger than 140 meters, any of which could trigger regional devastation. Likewise, supervolcanoes like Yellowstone or Campi Flegrei possess the capacity to inject over 100 cubic kilometers of ash into the atmosphere, disrupting climate and agriculture for decades. Continuous monitoring through seismic networks, satellite interferometry, and geochemical gas analysis is therefore critical to reducing planetary vulnerability. The European Space Agency's Near-Earth Object Coordination Centre now tracks over 1,200 potentially hazardous objects in real time, providing an early warning framework humanity has never possessed before. Technological self-destruction remains the most unpredictable filter. Artificial intelligence, synthetic biology, and autonomous weapons could trigger rapid, cascading crises if mismanaged. The Centre for AI Safety 2023 and Oxford's Future of Humanity Institute classify misaligned artificial intelligence as an existential risk comparable to nuclear war. Synthetic biology, particularly gene-drive technologies, could inadvertently collapse ecosystems if deployed without global safeguards. Coordinating international protocols, enforcing transparency, and fostering collective ethical frameworks is no longer optional. It is a prerequisite for survival. Experts estimate that autonomous weapon systems could be developed and deployed by 2030 inches regions, lacking coordinated oversight, presenting high-stakes geopolitical risks. Cosmic perspective also reframes our strategy. Expanding civilization beyond Earth is being pursued via NASA's Artemis program, SpaceX's Starship, and China's Lunar Base Initiative, which aim to establish sustainable extraterrestrial settlements within the next 20 years. Models from the Planetary Habitability Laboratory at the University of Puerto Rico indicate that miscalculations in closed-loop habitats could lead to system failures within 30 years, depending on atmospheric control, food production, and water recycling efficiency. Mars's lower gravity and thin atmosphere complicate agriculture and radiation protection, while lunar regolith is toxic to humans over long exposures. Historical and geological lessons provide measurable context for planetary integration. Mass extinctions, from the Permian-Triassic event 252 million years ago to the end Devonian collapse 360 million years ago, demonstrate ecosystem collapse under rapid environmental stress. Paleontological evidence shows that 70–90% of species disappeared during these events, and modelling of societal collapse indicates that deforestation, soil degradation, and prolonged drought can reduce agricultural output by up to 60% in affected regions. Preparing for the next filter requires measurable transformation. Civilization must implement resilient, systems-aware policies in urban infrastructure, energy, and food systems. Urban redesign should reduce energy consumption by 30% per capita and increase green space coverage to at least 25% in megacities. Biodiversity protection targets include conserving 30% of terrestrial and 30% of marine ecosystems by 2030. Global treaties, such as the Paris Agreement and the Outer Space Treaty, provide frameworks, but enforcing compliance and scaling them to planetary challenges remains a technical and logistical task. The stakes extend beyond survival. Modeling studies suggest that failure to reduce global carbon emissions and ecological degradation could result in a 25–40% collapse of the human population by 2100, with long-term biodiversity loss persisting for millennia. Conversely, successful mitigation could stabilize ecosystems and maintain global population growth projections at 9–10 billion by 2100. The challenge is profound. Quantitative modeling indicates that coordinated climate, energy, and biodiversity policies could reduce global systemic risk indices by up to 60% by 2100. Earth's record, the legacy of humanity. Every civilization leaves traces, and humanity is no exception. Long after cities crumble, satellites burn in the atmosphere, and digital networks vanish, Earth will retain chemical, isotopic, and structural evidence of human activity, detectable in sediments, rocks, and other geological formations. If scientists, human or otherwise, were to analyze sedimentary and igneous formations 10 million years from now, the record of the Anthropocene would be unmistakable. One of the clearest markers is the carbon isotope anomaly. Fossil fuel combustion has altered the global 1O cube C divided by 1O quadri C ratio by roughly 1.5 Ure since the Industrial Revolution, a spike that is already detectable in polar ice cores, ocean sediments, and peat deposits. Future geologists would observe a sudden depletion of 1 cube C across global stratigraphy, coinciding with the mid-20th century, and recognize it as a signature of rapid industrial activity. Similarly, nuclear activity has left a radioactive fingerprint that will endure far longer than any organic remnant. Plutonium-244, with a half-life of 80 million years, and Americium-243, with a half-life of 7,370 years, are now distributed in sediments, soils, and even deep-sea deposits from nuclear testing. Tens of millions of years into the future, these isotopes could serve as precise markers of technological activity, providing a temporal anchor within the geological record. Another layer of our legacy will be synthetic polymers, a category of materials virtually absent from pre-industrial strata. The plastosphere fragments of polyethylene, polypropylene, and polystyrene fused into sedimentary matrices is forming today in riverbeds, beaches, and shallow marine deposits. Known as plastiglomerates or plasticrusts, these materials can solidify into rock-like composites under pressure and heat. Their presence in ancient layers would be unmistakable, a clear signal that a technological species had chemically altered the environment. In parallel, microbial evolution is already responding to these synthetic compounds. Certain bacteria, such as Ideonella sacchiensis, have developed the ability to digest PET plastics. Future scientists could trace these evolutionary adaptations as biological markers of anthropogenic influence, revealing how life itself responded to civilization's chemical footprint. Infrastructure, too, may leave surprising geological legacies. Concrete, when subjected to heat and pressure over millennia, recrystallizes into mineral phases such as tobermorite and portlandite, forming materials that are far more durable than ordinary rock. Monuments like the Hoover Dam, the Golden Gate Bridge, or Mount Rushmore, and even underground metro systems like those in New York, London, or Tokyo, could persist as distorted but recognizable anomalies hundreds of thousands of years into the future. Deep mines and tunnels carved through Precambrian bedrock, including the Grasberg mine in Indonesia and the Mponeng gold mine in South Africa, might survive indefinitely, providing literal cross-sections of industrial activity. Unlike ephemeral surface structures, these subterranean features offer the possibility of direct stratigraphic evidence for a technological species. Our atmospheric impact, in contrast, may be even more persistent. The global CO2 concentration has risen from 280 parts per million in 1750 to over 420 parts per million in 2024, a 50% increase in less than 3 centuries. This surplus will delay natural carbon sequestration processes, including weathering, sedimentation, and oceanic uptake, for tens of thousands of years. Consequently, ocean chemistry, sediment composition, and even carbonate deposition will bear the unmistakable signature of industrial emissions long after humanity has vanished. Similarly, anthropogenic nitrogen and phosphorus fluxes resulting from industrial agriculture have increased by over 200% in some watersheds, creating isotopic and mineralogical markers that could persist in lake sediments and deltas for millennia. Elevated methane emissions, now at 1.9 parts per million double pre-industrial levels, will further alter redox conditions in soils and sediments, leaving detectable chemical fingerprints for millions of years. These layers of evidence constitute a planetary archive. Shifts in isotopic ratios, plastics in sedimentary rocks, and mineralized remnants of concrete provide a multi-dimensional fingerprint of human activity. Our digital and cultural legacies, by contrast, are far less durable. Data stored on current magnetic media, SSDs, or optical disks decays within decades or centuries without maintenance, and server farms themselves are vulnerable to climate and resource disruption. Even sophisticated satellite constellations, such as Starlink's 5,000-plus orbiting units, will re-enter the atmosphere within centuries, leaving only trace debris. In the deep time perspective, our chemical and geological imprints far outlast the ephemeral constructs of our culture, literature, and history. Even monumental libraries, such as the Library of Congress or the National Library of China, face decay or loss over millennia. These remnants provide evidence of human industrial, chemical, and construction activity. Isotopic anomalies, plastiglomerates, and concrete relics reflect technological capabilities and large-scale environmental modification. The notion of legacy also extends to biodiversity. Human-driven extinctions, now estimated at 100 to 1,000 times the background rate, will be preserved in fossils, bones, and DNA fragments, particularly in sedimentary basins like the La Brea tar pits or the Messel pit equivalents. Future paleontologists might note sudden reductions in megafauna, such as elephants, whales, and rhinoceroses, alongside the rapid proliferation of synanthropic species like rats, pigeons, and domesticated crops. Such patterns will serve as additional signatures of a technologically dominant species. The Great Filter represents a boundary that civilizations must navigate. Geological and chemical evidence of human activity, including stone, sediment, isotopes, and fossils, will provide future observers with a record of industrial and ecological impact. The legacy of humanity is recorded in isotopes, polymers, mineralized structures, and altered ecosystems. These markers will persist long after other records, providing measurable evidence of human activity for millions of years. Sedimentary layers, ocean deposits, and terrestrial strata will carry detailed chemical, geological, and biological signatures, allowing future scientists to reconstruct industrial processes, environmental impacts, and species interactions with unprecedented accuracy.